Hello?
Hi, can you hear me?
Yeah, I can hear you.
I can't hear you. One second. Can you hear me?
Yes, yes. How about you? How about now? Can you hear me?
I can hear you.
Okay.
Now, live streamers.
Hello, Ramya.
Hi, can you hear me?
Could we show Josh? He is also online. Yes, I can hear you.
Okay. Shall I just try sharing the screen? Okay, it says host disable
Sure.
participant screen sharing.
No, just 1 second, Mr.
You have to make me the host, I think, co-host or something.
Can you just wait 1 second?
Yeah, sure. Amma, you were saying something, Josh is?
No, I disabled the waiting room. They can all enter.
No, Josh. Okay. Now they can directly join.
Yeah, even now it says host disable participant screen share.
No, I think
just 1 second.
Now, so maybe it will take.
So I'm going to make Rigidity Workshop as a host. Okay. Now you can make whoever want to share a screen, you can make them as a co-host.
Okay, so all I need to do is just make co-host.
Yeah, for example, you can click on Ramya on
So now,
participants.
can you try sharing your screen? You should be able to share your screen now.
Yeah, can you see the screen?
Yes. So I don't need to start the recording, right? I mean, you will take care of that, or?
No, can you press the recording? I paused it. Now you are the host, you are the controller. Can you start the?
Should I start now?
Just there'll be a pause. 1 second. I think.
Yes. I know. I can see the recording paused. I can.
Yeah, click on that. Click on that.
Okay.
So now it's
recording now.
Yeah. So you don't stop the recording. Let it go for the up to 11 o'clock.
Oh, so now I don't. So I shouldn't stop the recording.
Don't stop the recording. And now you look at this thing. There is the last thing. Just 1 second, then we can start. There is a next to record. There is a more button. Is the 3 dots will be there. Can you see the 3 dots?
Next to yes, reactions. Yes.
If you click not next to reaction, there is the 3 dots.
Yes.
Click that. It will come stop live stream.
Yes.
So you press that. It will stop the live stream. Okay. If you want, you can stop it.
Okay.
Again, you want to start. You click the same button. For example, you can do it once if you want. You can do it once. Stop the live stream.
So I can stop and start at any time or multiple times, or do you?
can do it for a, yeah, you can do it anytime.
So should I do it now? Should I stop it now just to make?
Yeah, stop it and then you can start it again. There's no problem. Yeah. So yeah, again, you are on custom live stream. There is some small problem when it goes to 14th day, but actually it correctly records on 13th day. Don't bother about it. Huh? So if you go to YouTube.
Now I just see a web page redirecting to live stream page, and
so that's, I mean, that you can close it after a.
Okay, so now I see the YouTube thing.
No, but that is written there's some small issue. It says matrix rigidity 14th December.
Oh, I see.
But that is correctly, I can see the live stream here.
Okay. So I don't need to worry about that.
So you don't need to do anything. Just you can close that.
Start a live stream in 4 minutes. Is that correct?
Sorry?
If you start the live stream in 4 minutes, is that correct? Or 3 minutes now?
You just close it. That you can close it in that window. You can close it. It's already.
I close the YouTube window.
Yeah.
And now we are good.
Yeah. So if you don't have any trouble, you let the YouTube window also run. Let it run.
Okay. Okay, sounds good.
Just wanted to check. Can you see the pointer?
Yes, I can see the pointer, the red pointer.
Yeah.
as well as the hand.
Oh, you can see both, is it? Okay, then maybe I can.
Uh, Sorry, what is your name? Rigidity workshop. I forgot your name.
So my name,
Yeah.
Amay. Amay.
Amay, you can make any people co-host. Okay, so if you have any problem, you make more than one person as a co-host. Don't only because there is any internet connectivity, then there will be a problem. Make multiple people.
Okay. Yeah. So Mrinal will also join. So I'll also make him a co-host.
Many people as a co-host. Yeah.
Hello, Meena.
Hello, Amir. Yeah.
Can you hear me
Hi,
well?
Ramya. Yeah, I
Hi,
can.
hi.
Okay. How are you?
Yeah, doing good. Yeah, I thought I was a bit late joining and I had to search for the link.
Oh, okay. Should we post the link on the Slack channel? I don't know.
I didn't see it on the Slack channel, so then the Slack channel has, I think, the YouTube.
Yes, yes. So I shared the.
Oh, maybe it is on the.
It is on the general Slack channel.
On the general, there is a PDF which has all the links.
Right.
Should I share it on this workshop channel?
No, I think it is fine there. It's just that I had forgotten and I had to reread through 3 mails to find out in which mail it was there.
Amay, you can add the on your workshop Slack channel. You can add this link.
On the workshop Slack channel, that would make sense. Yes.
On this link, only this.
Only this workshops, right?
Yeah.
Ramya, are you currently in Mumbai or in Chennai?
Chennai.
Chennai. You have been in Chennai since March?
Yes.
Okay. Since we are all working from home, we cannot assume what the coordinates are.
I came here in March also.
Hi, Satya.
Hi, Meena. Hi, everybody.
Hello. Hi.
Good to see you guys here.
Yeah. It's been ages since we met.
Well, yeah, I guess for some time this is the way we meet. And yeah, I guess we get to meet more people this way, but
Meet, but the meet is in quotes.
Yeah, exactly. Yes. Yeah, I was actually looking forward to going to Goa for this conference. So where is the next FSTTCS going to be? Do you know? Do you guys know? Anybody?
Hopefully Goa.
Oh, okay. 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 They take a rain check. Good. Yep.
Yeah, I mean, that will be nice. And hopefully next year we indeed can go, because it's not clear how mass the vaccine rollout will be by then, but I would guess that we can go.
Right. Hopefully, yeah. December seems long enough.
Yeah. So my clock is showing 8:01. I don't know where, I mean.
Right.
9:02.
Should we just wait for a minute and then start?
Yeah, that's fine. I mean, you decide, you say when.
Okay, so maybe we'll just wait for a minute and then we'll start.
Yeah, I'm sure some more people will be joining.
Right.
By the way, do we have any breaks between talks, or do we have basically marathon?
Yes, no, we have 10 minutes break between every two talks.
Oh, okay. Okay, good. All right. Thanks. So who is Rigidity Workshop? I'm sorry, I didn't. This is Amit? Okay.
Ame.
Oh, Amit. Okay, okay.
Amit, I think, is not yet here. It is 3 a.m. where he is, no? 3:30 a.m.
Oh, okay. Right. That's true. Yeah. Okay.
And yeah, Josh is already here, but Mrinal I don't see yet. No?
Now said he'll join in a minute. I mean,
he will join soon. Yeah.
So, by the way, Ame, I have a silly question, and I hope other people don't mind me asking this question. How do you pronounce your last name?
Exactly. I mean, I get this question many times. So, right. So,
Bhangale or Bhangle?
it's Bhangar.
Bhangale. Okay, good. I'm glad I met you and I asked you that question, because I was always confused how to pronounce.
So you got the vowels right, but the last consonant or the semi-vowel consonant you have to work on.
Yeah, so I think that
The L.
Oh no, that I'm not going to work on. I don't think I'm going to succeed in working on it. No, I got that. I got that subtle distinction, but I think that I'm not going to train myself before tomorrow on that. But the vowels, I think, is more important because I had made that mistake before. So
What it's called iambic, right? You stress the second syllable, not the first.
I don't know.
The
Yeah,
iambic meter. Mm.
I see. Yeah. Mm. Yeah, until now I was pronouncing it as Bhangle, and then somebody told me, you want to check that.
right. No, I mean, most people say Bhangle, but
Yeah, if I hadn't met you, maybe I would have made that mistake tomorrow. But yeah, I'm glad that time.
I see Sasha has joined. Hi.
it's,
Hi, Bina.
Hey. Yeah.
Hi,
Hi.
hi, Sasha.
Hi, Satya.
should we start now? Okay. So I will start. So good morning, people from India. Welcome to this workshop on matrix rigidity. And my name is Amay Bhangade, one of the organizers of this workshop. We will start this workshop with a couple of tutorials, which will help the audience to get acquainted with the notion of rigidity. And please do check the Slack channel and the webpage of the workshop. You can find the link to the webpage in the Zoom chat box. I just posted it. And the talks will also be live streamed on YouTube. And feel free to interrupt during the talks for questions. The more interactive this workshop is, the more interesting it will be. And you can also type your questions in the Zoom chat box during the talks. And so just to say a few things about matrix rigidity, as we'll see in 2 days, rigid matrices are really interesting as they imply lower bounds for circuits in communication complexity, in data structure, and many other fields. And although we know rigid matrices exist, obtaining explicit rigid matrix has remained a long-standing open question. And also a recent line of work showed that many previous leading candidates for rigid matrices are actually not rigid enough. And on the other hand, a highly non-trivial construction of rigid matrix was shown in the last year. And we'll talk more about it in the coming talks. So that's it. And without further ado, let me hand it over to Meena, and Meena will chair today's session. So Meena, please.
So welcome everybody to this session. I'm pleased to be chairing this session, and I would like to thank the organizers for putting together this workshop at all in the first place. It's like a great, very relevant theme to have right now, to listen to right now. So we have 3 talks for today. The first 2 talks are going to provide a nice kind of overview, background. So they're listed on the conference schedule as, on the workshop schedule as tutorial. But here I see that the title slide has a more interesting title there with, although there is no snow in Chennai and there is no snow in, where most of the organizers are. So anyway, it's my pleasure to introduce the first speaker, C. Ramya. So Ramya is currently a postdoctoral fellow at the TIFR in Mumbai, and her main research interest is algebraic complexity. She did her PhD at IIT Madras under the guidance of Raghavendra Rao, who incidentally did his PhD under my guidance. So I have a very direct connect with him. And her PhD thesis was also on multilinear circuit models and van der Waals polynomial. So she's recently written a nice survey on matrix rigidity, which is up on ECCC. So after the talk, people who would like to go back and see more details can look at the review or look at the survey. So now over to Ramya. Yeah.
Thanks, Meena. And first of all, thanks to the organizers for this wonderful workshop. And thanks to everyone for stopping by matrix rigidity. Just as Amay mentioned, this is the first introductory tutorial on rigidity. This will be followed by another talk by Golovnev. So both these talks are designed to provide fundamentals of rigidity and also just discuss some advances so that the rest of the workshop is quite interesting and accessible. Okay, so let me get started. So matrix rigidity is a concept that was introduced by Valiant about 40 years ago in the year 1977. It was introduced in the context of computing linear transformations by arithmetic circuits. It was also studied independently by Gregorio in the year 1976. So what is rigidity of a matrix? Let's say you're given a matrix A, say an n by n matrix with entries from a field F, and you're also given a target rank R. The rigidity of a matrix A for rank R is the minimum number of entries you have to change in A so that the rank of A is reduced to R. It's a very simple notion. We'll see more about rigidity. So throughout this talk, for any matrix A over the field F, we will denote the rigidity of a matrix A for rank R by RA of R with the superscript F. Sometimes if the field is clear from the context, then we may drop this superscript just to make it notationally convenient. Let's begin with a simple example. Let us say we consider the n by n identity matrix. Then for any target rank R, you can flip n minus R of the diagonal entries from 1 to 0, and you can always reduce the rank to R. So the rigidity of the identity matrix for rank R is at most n minus R. Moving on, what are rigid matrices? You say a matrix is rigid if it not only has high rank, but if you want to reduce its rank to smaller value, you'll have to change a lot of entries in the matrix. It's not very fragile, it's very rigid in that sense. So intuitively, this also means that rigid matrices are quite far from matrices of low rank. So two things that are not defined here are far and low. We'll do that slowly during the course of the talk. Another way to look at this quantity RA of R is that because it is the minimum number of entries you are changing in the matrix A so that the rank is reduced, it is essentially the Hamming distance between the matrix A and the set of all matrices of rank at most R. So what makes rigidity a very interesting aspect that it deserves to find a workshop at FSTTCS? The first important thing is that it's one of those very few properties that we come across that has two flavors in it, one a combinatorial flavor and another an algebraic flavor. This is because Hamming distance is a very combinatorial property and rank of matrices is a very algebraic property. And because rigidity measures the Hamming distance between the given matrix and set of all matrices of bounded target rank, rigidity intertwines a combinatorial as well as an algebraic property. This makes rigidity very interesting, but it also makes rigidity quite hard to understand at the same time. As Amai mentioned, the other interesting aspect of rigidity is that it has many interesting connections to communication complexity lower bounds, data structure lower bounds, coding theory, and so on. And these connections will be discussed in Golovnov's talk. For this talk, we will look at the fundamentals of rigidity. Okay, so let us try to interpret rigidity in slightly greater detail. Suppose you're given a matrix A, which is an n by n matrix with entries from the field F. And let us say the rigidity of A for rank R is at most S. What does that mean? It means that by changing S entries in the matrix A, you can reduce its rank to a value less than or equal to R. Right? Which means that there are these marked positions in A where if you change the AIJs to BIJs, you can reduce the rank to R. This immediately means that there exists a matrix C, which can be seen as a change matrix. It measures the amount of change you have made, where the ijth entry is Bij minus Aij if this position is marked and 0 otherwise. It's a very simple matrix that you can define from this, but it has two interesting properties. The first is that the number of non-zero entries in C is at most S. And the number of non-zero entries in any matrix is called the sparsity of the matrix. This is because there are only S marked positions here. So by the definition of C, there will be only S non-zero entries in C at most. And the second important property is that the rank of the matrix A plus C is bounded by R. This is because the rank of A plus C is essentially the matrix A with the Aijs flipped to the Bijs, the corresponding positions. So the rank of A plus C is at most R. So what did this discussion give us? Whenever the rigidity of a matrix A for rank R is at most S, there exists another n by n matrix C whose number of non-zero entries or sparsity is bounded by S, and rank of A plus C over the field F is at most R. Now in the other direction, if there exists a matrix C, which is also an n by n matrix with entries from the field, whose sparsity is at most S and the rank of A plus C is R, then you look at the matrix A and you change the entries of A to the entries guided by A plus C. You will change at most S entries because the sparsity of C is at most S, which means that by changing at most S entries in A, you can reduce the rank to R. This means that the rigidity of the matrix A for rank R is at most S.
Would you just go on to why the rank of A plus C was at most R again?
Okay. So you consider this matrix A plus C. What is A plus C? A plus C is exactly the matrix A with the Bij's flipped to the Aij's flipped to the Bij's, right? If you look at the entries, this is Aij, this is plus Bij minus Aij.
Oh, yeah.
So
yeah. Oh,
you assume that the rigidity of the matrix A for rank R is at most S.
yeah.
Is it answered?
Yeah.
Okay. Okay. So what does this give us? Right? This gives us a very mathematical formulation of rigidity. The rigidity of a matrix A for rank R is the minimum sparsity of a matrix C, such that C is an n by n matrix, which also has entries from the same field as A, and the rank of A plus C over the field F is at most R. This is essentially the mathematical way of saying that rigidity is the minimum number of entries you have to change in A so that the rank is reduced to R. So we just decoded that English statement to math. So let's, this is something that is important to keep in mind, and this definition will come quite often. So let's stare deeper at this definition. What do we get from this? Suppose the rigidity of a matrix A for rank R is bounded by S, then you can write, you know that there exists a matrix C such that its rank is at most, rank of A plus C is at most R. Let's call this matrix A plus C as L, right? Where L means that I'm just using L to say that it has low rank or bounded rank. This immediately means that when you can write A plus C as L, right, you can write A as a sum of a sparse matrix and a low rank matrix, where the sparsity of S is at most L and the rank of L is at most R. In the other direction, if you can express A as S plus L, where S is a matrix of sparsity at most S and L is a matrix of rank at most R, then you can change the entries of A to the entries of A minus L, A minus S. You'll change at most S entries and you'll be able to reduce the rank to R. So rigidity of the matrix A for rank R is at most S. So this gives a very nice way of viewing matrices that have high or low rigidity. This means that whenever a matrix has bounded rigidity, you can decompose it into a sparse and a low rank matrix. So if someone comes to you with a matrix A and asks you, can you say its rigidity is bounded by this? All you need to do is just come up with a sparse matrix and a low rank matrix of appropriate sparsity and rank and say that I can write A as S plus L. Whereas if you have to show that some matrix is quite rigid, then you have to say that A can never be expressed as a sum of sparse and low rank matrix, which makes the problem slightly hard. So let's get back to the example that we saw. We did see that for an n by n identity matrix, the rigidity is at most n minus R. Incidentally, it's also exactly n minus R. Why is this true? Suppose the rigidity of the identity matrix is strictly less than n minus R. Then by this definition, you know that there exists a sparse matrix C whose sparsity is less than n minus R and rank of identity plus C is at most R. Okay? Now, if you look at identity matrix, it's a full rank matrix. By adding a matrix C to it, you cannot reduce its rank to a value smaller than, you cannot reduce it by a value smaller than the rank of C. So rank of identity plus C is at least this much. And the rank of C is bounded by n minus R. The sparsity, anyway, the number of non-zero entries in C was n minus R. So the rank couldn't have been larger, which means that the rank of In plus C is greater than R, which is a contradiction. So this gives a lower bound on the rigidity of identity matrices, which means that you'll have to change n minus R entries in the identity matrix in order to reduce its rank to R for any target rank R. Okay. So let's build on this simple observation that we have by constructing a slightly intelligent, clever matrix and also prove a slightly stronger lower bound. So consider the matrix on the right side of the slide, where you have identity matrices stacked. So along every row, you have 2R you have n by 2R many blocks, and every block is an identity matrix of dimension 2R. Similarly, on every column, you have n by 2R blocks, and every block is an identity matrix of dimension 2R. So there are totally n square by 4r square many blocks. Let's call this matrix Mn. It's an n by n matrix. I'm also going to assume that n is divisible by 2r just to make the diagram look neat. So this is a result from 2005 that the rigidity of this matrix on the right hand side for rank R is exactly equal to n square by 4r. Right? This proof is not very difficult, but let's quickly do this just to get a feel for rigidity. So the first thing to observe is the upper bound. Note that by changing R entries in every block, right, just by flipping the diagonal entries from 1 to 0, but you have to do this consistently in the sense that you have to touch the same rows in all the blocks. By doing this, by changing R entries in each block, you can reduce the rank of this matrix to R. There are n square by 4r square many blocks, and you're going to change R entries in each block. So the rigidity of the matrix M for rank R is at most this quantity. Now to prove the lower bound, we'll do what we would have done naturally. Suppose the rigidity is strictly less than n square by 4r, which this means that by changing much less than n square by 4r entries, you can reduce the rank to R. There are n square by 4r square many blocks, and you are saying that you have touched only fewer than n square by 4r many entries, which means there's at least one block where you changed fewer than R entries and you reduced the rank to R. But each block is an identity matrix of dimension 2R. So by the previous argument, you must have changed at least R entries. Right? So this contradiction gives an lower bound on the rigidity of this matrix. This means that for this nice stacked identity matrix, the rigidity is n square by 4r. Just a spoiler, that the best rigidity that we know today is just a logarithmic improvement of this. So we are already sort of there. Okay, so one question you might be wondering is how large can the rigidity actually be? Right? It can be at most n square, because if you're allowed to change all the entries in the matrix, you can put R ones on the diagonal and 0 everywhere, and you can always reduce the rank. Now what Valiant showed is that you can actually do much better. By changing n minus r the whole square many entries, you can reduce the rank to R for any n by n matrix and any target rank R. This is not a very difficult thing to see, but we are going to do this just to get. It's a very nice argument, and I think it's worth knowing. Suppose the given matrix already has rank less than or equal to R. You don't have to do anything, which means the rigidity is 0. If that's not the case, then you know that the rank of the matrix A is greater than R. This immediately means that there is a full rank submatrix of dimension R in A. Let's call this matrix P. For convenience, I'm also going to assume that this full rank submatrix is in the top left corner. I'm going to sort of permute the rows and columns and push everything to the top left corner. And the other matrices, I'm going to call them C, D, and E of appropriate dimensions. First observation is that because this matrix P has full rank, every row in D, you can write it as a linear combination of the rows of D. In fact, you can write it as a unique linear combination. See, the first row of D can be expressed as alpha 1 times the first row of B plus alpha 2 times the second row of B, and so on. This is a simple observation that we can make. Let's build from this. Now, you can change the entries in E according to the linear combination that we just saw. That is, you look at the first row of E and change the entries to alpha 1 times the first row of C plus alpha 2 times the second row of C plus so on till the alpha R times the rth row of C. So what did we just do? In the end of this process, we have expressed every row of A, at least the R plus 1th row of A, as a linear combination of the first R rows of A. Right? Similarly, the R plus 2th row of A, you can express as the first R, a linear combination of the first R rows of A, and so on. And what are the entries that you changed? You only changed the entries in this matrix E. And E, if you remember, is an n minus R by n minus R matrix. So by changing n minus R the whole square many entries, you reduce the rank of A to R. This means that the rigidity of the matrix A for rank R is bounded by n minus R the whole square.
So these alpha i's were coming from the matrix D, right?
These alpha i's, so you look at
They're
D.
coming from the linear combination of D with respect to B.
Exactly. You use the same linear combination and edit E.
Yeah.
But the only entries you have changed are the entries in E. You didn't touch anything else.
Yeah.
So by changing n minus R the whole square many entries, you could reduce the rank.
Yeah. Okay.
So This is a very nice argument. So I thought I'll just put this here. Oh. So if there are any questions so far, maybe we can discuss that. Else we move on to the second part, which is about how Valiant introduced rigid matrices or how they were actually born. Are there any questions so far? Okay, so let's just move on. To discuss how Valiant actually came up with rigidity, we need to understand a very simple model of circuits. It's called linear circuits. This is quite simple because the only operations you are allowed are additions and scalar multiplications, nothing.
I have a question. Can you go back to the last slide? So if I just take this matrix E and make them say, and they take the negative of all this, why will that not make this E all zeros and then the rank becomes at most R? Why do you need to do this linear combination of alpha 1 rho 1 C and so on and so forth?
So you would change just n minus R the whole square many entries, but the rank would not be R, right? Most R. By just zeroing out E, right? Is
yes.
that the question?
Yes.
The rank would not be reduced to.
I mean, it may be possible that whatever D is sort of independent compared to B.
Yeah.
So maybe the rows D are adding more to the rank.
Yeah. This could be like 0, 1 vectors, which are all independent, and this row could be completely independent from this, in spite of the elements in E, the first row of E being 0.
It might be 2 times R, right? The rank. Oh, but we want to reduce the rank to R.
R.
Okay.
Does that answer?
Yeah, thank you.
Okay, so let's get back to linear circuits. So what is a linear circuit? The picture on the right side is actually a linear circuit. But more formally, a linear circuit is a directed acyclic graph. You consider all gates of in degree 0. These will always be labeled by variables, say x1, x2, x3, and so on. And every gate gate with in degree more than 1 is an addition gate. There are no other operations that are involved. Apart from this, you can also label the edges with some constants from the field. These help us do scalar multiplication. So this gate computes 2x1 plus x2 and so on. So if you look at the linear circuit, we'll usually consider linear circuits where the number of inputs is, let's say, n. So variables are x1 to xn. Some of these gates, we'll call them output gates. And each of these gates compute linear polynomials. So if you look at this circuit, it computes 8x1 plus 3x2 and 7x1 plus 5x2. You can view linear circuits as computing a linear transformation. It takes this x vector to A times x, where the matrix A is defined from the coefficients of these linear polynomials, just like I've written it here. This is something we would do naturally. Throughout this talk, we will look at linear circuits where there are n inputs, n outputs, and every gate has fan into. So this is the model of linear circuits we will be looking at. So here is a simple example of a linear circuit. There are n inputs L1 to Ln, n inputs x1 to xn, and n outputs L1 to Ln. And every gate has fan into. So you can think of linear circuits as computing a linear transformation, just like we saw in the example. And every such transformation can be naturally associated to a matrix A, which is an n by n matrix with entries from the field F. With respect to linear circuits, we'll be interested in 2 parameters. One is the size of the circuit, and the other is the depth of the circuit. Size is the number of edges in the circuit, and depth is the length of the longest path from input to output. So here it's depth 2 circuit. So we did see that linear circuits can be seen as computing linear transformations from F to the n to F to the n. How large can its size and depth be? Because you're computing n linear polynomials and each polynomial is on n variables. Any linear transformation can be computed by a circuit of size order n square and depth order log n, because the fan in is 2. Since there are circuits, we need to discuss lower bounds. The best lower bound that we know is linear lower bound. This is due to Chashkin from 94. It is a lower bound of the form 3n minus log of n. For an explicit matrix, we need to define what explicit known is, but the best known lower bound is something linear. That's something to keep in mind. So this brings us to 2 questions. The first question is, can we prove superlinear lower bounds? For linear circuits, when I mean superlinear lower bounds, superlinear size lower bounds. For linear circuits, when the depth is logarithmic. The second thing is, we have naturally now associated matrices to linear circuits. So in the context of rigidity, you might want to ask, what can we comment on the linear circuit complexity of rigid matrices? That is, if you have a matrix that has very high rigidity, can it be computed by small size, small depth linear circuits? So in this context, these two questions were studied by Valiant in 1977 in the same paper where he introduced rigidity. What he simply says is that rigidity lower bounds imply linear circuit lower bounds. In other words, if you have a matrix A that has super linear rigidity, that is, you'll have to change at least n to the 1 plus delta many entries in order to reduce the rank to, say, epsilon n, where epsilon delta are constants. Then, if you look at the transformation that is represented by this matrix, and if you want it to be computed by linear circuits of logarithmic depth, it must have size superlinear. So what does this tell us? This tells us that rigid matrices cannot be computed by linear circuits that have small size as well as small depth. If you're restricting the depth to log n, the size has to be superlinear. And now we sort of know what high rigidity is. High is superlinear. Low is anything smaller. I mean, this is something we didn't do in the beginning of the talk, which we are now familiar with. Okay. So I want to quickly present a proof of this. It's a very nice proof. So we will try to prove the contrapositive of this. That is, if you have a linear circuit that has logarithmic depth and size n log n, then its rigidity of the matrix computed by the circuit is at most n to the 1 plus delta. So consider a linear circuit where size is S, depth is D, n inputs, n outputs, and the fan in is 2. For proceeding further, we will need a nice result from extremal graph theory. This is due to Erdos, Graham, and Semeridi from 1976. We will not prove this. We are just going to use the statement off the shelf. This talks about removing edges in a directed acyclic graph. So linear circuits are nothing but directed acyclic graph. So what this statement says is that if you have a directed acyclic graph that has S edges and the path length of every path in the graph is at most D, then by removing S by log D many edges, you can ensure that the resulting graph has path length at most D by 2. That is, you can reduce the path length by half every time by removing S by log D many edges. So repeating this edge removal process epsilon times, we'll be able to ensure that the length of every path is at most D by 2 to the epsilon, and the number of edges removed is this much. I'm just going to do this again and again. If you recall, we had n outputs in the linear circuit, but we are just going to look at one output and then think of what to do with the rest of the outputs. Let's look at the ith output. We did remove some edges and some of them were retained. I'm just denoting the removed edges by dashed edges. And let's call the tails of the removed edges as B1, B2 to Bk. We know that the number of removed edges is at most S epsilon by log D. By tail, I mean the vertex from which this removed edge originated. The first observation to make is that every such Li is a linear polynomial, and every such linear polynomial can be expressed as a linear combination of these Bi's and the remaining input variables. Some of them might be removed, but whatever remains, that and Bi's. This is not a very difficult thing to see. If you probably stare a bit more at the linear circuit, you'll be able to get that. So once we have this, what do we get? Every such Li can be written as a linear combination of the tails and the remaining input variables. The number of variables that remained is this much, because every gate at fan in 2 and the path length is bounded by D by 2 to the epsilon. This was just one output gate. Actually, you had n output gates, so you'll have n expressions of this form, where each Li you can write it as a linear combinations of B1 to Bk and a vector C, which has sparsity this much. This sparsity is exactly the number of input variables it remains. Is this clear so far? Okay. Now, since we have n equations, you can express this as in the form of matrices. And let's call these matrices A, B1, B2, and C. So this matrix is essentially the matrix that is computed by the original linear circuit. You had LIs on each row. This is the matrix that was computed by the circuit. Let's call it A. And B1, B2, and C do the following. So each Li is dependent on the Bi's. This dependence is captured by B1. These Bi's depend on the input variables. That dependence is captured by the matrix B2. And the dependence of Li's on the input variables is captured by the matrix C. And the dimensions of B1, B2, and C are here. So this intuitively means where we are going to, right? We are trying to write A as a sum of a sparse and a low rank matrix. So the rank of B1, B2 is bounded by K just for dimension reasons. And K is the number of tails. That's at most S epsilon by log D based on the removal process. And if you look at the matrix C, every row here had sparsity this much, and there are n rows. So the sparsity of C is at most n times 2 to the d by 2 to the epsilon. So the rigidity of the matrix A for rank R for this rank, right, is at most n times 2 to the d by 2 to the epsilon. Now what I'm going to do is I'm going to substitute S as n log n and depth as log n, because that's the context that we are interested in. Then this would evaluate to something like n to the 1 plus delta. This is something like epsilon n. So if you have a matrix A that is computed by linear circuit of size this much and depth log n, then the rigidity is bounded. So this proves a Welian statement that if you have superlinear lower bounds on rigidity, then any log depth linear circuit computing this matrix A must have size superlinear. So this brings us to the central question that we'll be interested in this workshop, is to find a sequence of matrices that have superlinear rigidity. Or more formally, you have to find a sequence of matrices which are all n by n. They have entries from the field, and the rigidity of the matrix M for rank epsilon n is at least n to the 1 plus delta, where epsilon and delta are constants. So something that I've not defined here is the word explicit. By explicit, we mean that you should be efficiently able to compute the entries of the matrix, or there is a deterministic algorithm that runs in time polynomial in n, whichever when given as input n in unary, it will output all the n square entries of the matrix. So such a matrix is said to be explicit. And what Welian does is that can we come up with an explicit sequence of matrices that have superlinear rigidity?
Question.
Yeah.
So the algorithm has to output the entries, but in what form?
I believe this would mean in binary.
As a bit representation.
Yeah, bit representation. But I'm not very sure about this.
Okay, okay.
I think this would mean the bit representation of the entries. Yeah, so we will see some places where we won't be able to output the bit representation. They are non-explicit. So I'm going to say that whatever is the number, the binary representation of that should be, you should be output that in polynomial time.
Question. The Edos-Zimmermann-Graham theorem, is that constructive? The proof, does it give you the set of edges to delete?
No, so as far as I know, I think it says there exists a set of edges that you can remove, but I don't know if there is a constructive version of that.
Here, what do you mean by there exists a deterministic algorithm on input 1 raised to n? What does the input 1 raised to n thing mean?
So you will input the number n in unary. So instead of inputting the binary representation of n, suppose it's 3, you will give as input 3 ones. So the number n is input in unary. That is because you want the running time to be polynomial in n.
Okay.
So if I input the bit representation, right, that's only a log n length string. So then poly is exponential in input, right?
Mm-hmm.
For that purposes, we'll usually say the input is in unary, and I want the algorithm to run in time polynomial in n.
Okay. Yeah.
Yeah, I think now, it should be you should output the bit representation.
Okay. Yeah.
That question also answers that. Okay, so what is this workshop going to be about? We're going to try and see how to answer Welian's question. This question was posed in 1977 and it remains open. So I think this requires effort. But we have seen a lot of progress towards answering this question, and that's what we will see in the rest of this workshop. I think there is some time. So just as Amay mentioned, we do know that there exist rigid matrices. What do we mean by that? We know there are matrices where you'll have to change, there exists matrices where you'll have to change a lot of entries in order to reduce its rank, but we don't know how to find that. That's the problem. So the existence of rigid matrices was proved by Variant himself in the same paper in which rigidity was defined. Let's first answer this question for finite fields. So suppose F is a finite field of size Q, then for any target rank R, where R is within this range, you can be sure that there is a matrix, n by n matrix with entries from the field, such that the rigidity of the matrix M for rank R is something close to the upper bound that we saw. We did see that for any matrix, it's at most n minus R the whole square. We do know that there exists matrices that have this rigidity. So I would want to quickly go over this proof. This is a simple proof as usual by counting. Suppose you have the set of all n by n matrices with entries from the field FQ. This is a set of size like q to the n square. Now what I want to say is that if you consider the set of matrices whose rigidity is bounded by S for rank R. So S here is n minus R the whole square by log n. I've just written S so that it's easier to write here. You look at this set and you count the size of the set. If the set is q to the n square, then you know that there is a matrix M outside the set. That's what we are going to do. For this, we are going to use the fact that whenever the rigidity is bounded by S, we know that we can write A as a sum of a sparse and a rank R matrix. So to count this set, you need to count the number of S sparse matrices and the number of rank R matrices. For this, to count the number of S sparse matrices, first you have to choose S non-zero entries. And then you have to, for each of these non-zero entries, you have Q choices. So the total number of S sparse matrices is this much. To count the number of rank R matrices, if you recall, we did see this picture, right, with B on the left and then C, D, and E. So whenever the matrix has rank R, first you can choose the positions of B, which are these many, and then you're allowed to choose the positions for the submatrices B, C, and D. The bottom rightmost matrix can be expressed as a linear combination. So there are these many choices for the submatrices B, C, and D. This will give a count on the number of rank R matrices. So together, the number of matrices of rigidity at most S for rank R is this. I'm not going to the details of this counting. I think it's a fairly easy exercise. But still the numbers are here. So now by plugging in R to be a value that is in this range and S strictly less than n minus R the whole square by log n, this quantity will evaluate to something like order 1 by n times q to the n square. So only 1 by nth fraction of the total set of matrices have rigidity less than S, which means that there exists a matrix of rigidity n minus R the whole square by log n. And in fact, many matrices have this rigidity. As n increases, this fraction becomes smaller and smaller. The fraction of non-rigid matrices or the size of the dark blue set in the picture becomes smaller and smaller. So we do know that there are matrices that have high rigidity, but we don't know how to construct them in polynomial time. This is what Amay mentioned in the introduction. So what does this counting give us? Did we do this exercise just to count? Not really. So this gives us a first construction of rigid matrices. You know that they exist, just brute force search for them. Right? So what you do is for every n by n matrix A, whose entries are in the field, test if the rigidity is bounded by S. How do you do that? You test whether there exists an S sparse matrix C such that the rank of A plus C is bounded by R. This just follows from the definition. So you're going to run over all n by n matrices over finite fields. So this requires time q to the order n square. And all sparse matrices, this requires q to the s time. And then polynomial time to do this. Okay. So this is the running time. We are going to call this super exponential time. Might not be very standard, but still it's q to the order n square. So even over f2, this will require 2 to the order n square time. But nonetheless, this is the first construction we've seen in this talk. An analogous statement also holds for infinite fields, though the proof is slightly involved. It's not just counting, but I've just mentioned it here in case people want to know. Right? So you can also find a super exponential time construction over infinite fields. So now that we know rigid matrices exist and I want to construct one, what would be the first natural candidate to think of? Suppose you have an n by n matrix, all of whose submatrices, let's say, have full rank, right? All of whose R by R submatrices have full rank. Then, if you change very few entries in the matrix M, there will be at least one submatrix that you didn't touch, because all the submatrices are full rank and you change really, really few entries. And this one submatrix that you didn't touch will contribute a rank R. So intuitively, this means that matrices that have this property are potentially rigid. So let's try to work with them. So one question, the first question that might come to your mind is, do such matrices exist? Right? Do we know of matrices like this? We do know of matrices that have this property. They're called totally regular matrices. And one example of such a matrix is the Cauchy matrix. So let's consider a field where there are 2n distinct elements, x1 to xn and y1 to yn. And the ijth entry of the matrix is 1 by xi plus yj. It's not very difficult to see that this matrix has this property. Any size you choose and any size submatrix, it will have full rank. And another nice thing to note is that this matrix is explicit. Right? In polynomial time, you can construct this matrix. So this immediately leads us to a result from 1997, at least the second result that we are going to see. If you consider any field with at least 2n distinct elements, the rigidity of this matrix is omega n square by r times log n by r for target rank within a certain range. Okay. So one question here is that this result here, you need the size of the field to be at least 2n. The size is dependent on n. So there might be people who are not very comfortable with that, size being dependent on n. There is another result where which also works for constant size finite fields or constant size fields, where a similar rigidity bound is obtained, but that is this is due to Friedman, and that uses error correcting codes. And I believe this will be in the second talk by Coulomb. So this is an explicit matrix. This has omega n square by r log n by r rigidity. This is pretty much the best we know. This is constructible in polynomial time, and this is the rigidity bound we know. Recall that we wanted to show super linear rigidity. The best we know is something like this. But not much hope to lose. There is some more time, so we'll see more constructions. But let's quickly see a proof of this. Right? It's essentially what I mentioned here, but nonetheless, let's do this.
Hi, Ramya. I have a question. Hello?
Yeah.
You would say Vandermonde matrix, will that rank will not be high?
Yeah, we'll come to Vandermonde.
Okay, thanks.
Okay, but before that, let's see a proof of this. We'll come to Vandermonde slightly later in the talk. Vandermonde, as of now, there is one set of parameters for which it's open, I mean rigidity bounds. We'll come to that. So suppose the rigidity of this Cauchy matrix, yeah, I'm just calling the Cauchy matrix Mn, is much less than n square by r times log n by r. This means that you can change fewer than these many entries in M, and you can reduce the rank to R. Right? So we don't know what to do next, so let's try to draw a graph. We're going to represent the change we made by a bipartite graph. So consider an n by n bipartite graph where you draw an edge between I and j if and only if the ijth entry of the matrix is untouched. So since you changed fewer than these many entries, this graph has at least n square minus little of n square by r log n by r many edges. So this is quite a dense graph. How likely is it that this graph has a complete bipartite subgraph? That's the question we would want to ask. And for this, again, we will appeal to graph theory. where this is a theorem from 1954 which bounds the maximum number of edges any bipartite graph can have without having a complete bipartite subgraph. I'm not getting into the parameters here, but at least there is a maximum bound on the number of edges. And the number of edges in G is much more than this quantity. And this is where the actual bounds on R come. So in the original statement, there was a bound on R, right? R at least log n and at most n by 2. So for that purpose, we will need to bound the range of R. But since G has much more edges than this, G definitely contains a complete bipartite subgraph of size R plus 1. But what does that mean in our case? It means that we didn't touch R plus 1 by R plus 1 submatrix. Right? That's how we drew the edges. This means that the rank could be R plus 1. So it's never possible that you changed fewer than n square by R log n by R many entries and reduce the rank to R. So now slowly moving on to.
So what does the complete bipartite subgraph mean?
Oh, so it means you have two sets of, let's say you have an edge between this vertex to every other vertex in the subgraph. Okay, so let's say you have a R plus 1 by R plus 1 complete bipartite subgraph. It means that you have R plus 1 vertices on the left, R plus 1 vertices on the right, where there is an edge between this vertex and every other vertex here.
Okay.
There is no edge.
So from left to right, there is an edge from every vertex to every vertex.
Yeah. R plus 1 vertices here and R plus 1 vertices here.
Oh, okay, yeah.
So for the next construction, I think some time. Okay. I have about 15 minutes, 20 minutes.
A little less, I would think.
Okay.
Maybe,
okay, so,
yeah, 15 minutes, okay, because we did start a bit late, but 15 minutes would be including all the Q&A and so on.
Oh, okay.
We are asking the questions along the way, so that's fine.
Okay, so maybe I'll skip some details, but. Okay. So to see the next construction, we need to define a few things. Quickly, let me do that. Suppose you have n real numbers. You say these n elements over R are algebraically independent over Q if they do not satisfy any non-trivial polynomial equation. That is, there is no polynomial on n variables with coefficients from Q, such that by plugging in a1 to an in this polynomial, it will evaluate to 0. Then such elements are said to be algebraically independent. Here is an example. I have to quickly go over this. So a standard fact we'll use is that there's nothing special about elements here. You could do the same definition with polynomials. And any set of n plus 1 polynomials on n variables is algebraically dependent. In other words, if the number of polynomials is more than the number of variables they are defined on, then they're always algebraically dependent. So now using this, let's try to argue that if you have a matrix where the entries are algebraically independent over Q, these entries are reals, then the rigidity of the matrix A for rank R is exactly equal to n minus R whole square. This is really good because it just matches the upper bound that we have. Right? So one thought you might have is, have we answered Delian's question? Unfortunately not, but let's see a proof before that. So the upper bound just follows from Variance theorem. For the lower bound, suppose you are able to change fewer than n minus R the whole square many entries and reduce the rank to R, then by definition, you know that you can sum decompose A as S and L, where the sparsity is bounded by this and rank is bounded by R. Now, every entry of A is a function of the entries of S and the entries of L, right? Just because A is equal to S plus L. And how many entries are there in S? There are S entries. How many entries are there in L? Now I need to again appeal to the old picture that we had, this B, C, D, and E. Right? Every entry of E, you can express it as entry of B, C, and D. So the only entries that matter are the entries of B, C, and D, which are these many entries. So every entry of A can be written as a function of these many entries of L and S entries of S. Okay? And how many, so each is a polynomial function. You have n square many polynomials on these many variables. And when you say that S is much less than n minus R the whole square, the number of variables is fewer than the number of polynomials. So we will use the fact that we just said that these entries must be algebraically dependent. It's a contradiction. Right? We started with a matrix where the n square entries are algebraically independent over Q. Right? So, so why are we done? Like, have we answered Delian's question? Unfortunately not, because this matrix is not explicit. One way to see this is that if you look at the degree of the extension field where these n square entries lie, this is something like 2 to the n square, and the time to construct this matrix would be somewhat proportional to the degree of the extension. So this is not explicit. Another way to see this would also be that if you ask me to say the entries, it would be something like e to the root 2, e to the root 3, e to the root 5, and so on. And these are numbers that have infinite precision. Right? After the decimal point, you have infinitely many digits. So it's not possible that you can explicitly construct. So what do we do next? One way to do this would be to reduce the amount of algebraic independence, but have high rigidity. Along these lines, there were a couple of results from 2000 and 2006 by Satyalokam. The first one reduced the number of independence, right? That is from n square to n. How do you do that? You take n algebraically independent elements over Q from the complex numbers, and you consider the van der Waals matrix. The rigidity of the van der Waals matrix for rank R over complex numbers is something like omega n square, where the rank is at most order root n. So this definitely reduces the independence from n square to n, but it works for the rank being bounded. Right? The rank needs to be at most order root n. And when the rank is little omega of root n, we do not know yet if van der Waals matrix is high rigidity or not. So that is potentially a candidate, but we don't know how to go forward and prove it. And in the subsequent result in 2006, we completely got rid of algebraic independence by choosing the n square entries to be square roots of distinct prime numbers. You choose n square distinct prime numbers and take their square roots, fill up the matrix. This matrix has rigidity n square, the maximum possible you can think of. But then the problem is these are numbers with infinite precision, just as I said. So you cannot explicitly write them down. Yeah, so just to mention that we have come from algebraic independence to linear independence because square roots of distinct primes are linearly independent. And these results are proved via what is called the Shub-Smolenski dimension of matrices. We won't have much time to talk about it, but I think Bentley's talk might cover some details. Okay. So where are we right now? On one hand, we have polynomial time constructible matrices like the Cauchy matrix, but the rigidity is quite moderate. It's something like n square by r times log n by r. So when r is a function of n, this is not superlinear. On the other hand, we have matrices like this, right, which have very high rigidity. It's the maximum possible, but we don't know how to write them down efficiently, right? Construct them efficiently. So the battle is to find the middle ground, something that is explicit and also has superlinear rigidity. So in the remaining time, let's quickly go over what we have done in the 2000s. Right? At least so far we are in 2006. We need to move forward quickly in another 10 minutes. So one question you might have had is, what about random matrices? Right? It's not very difficult to see that random matrices are rigid with high probability. There are lots of rigid matrices we did see. There exist. So if you choose one uniformly at random, with high probability, it would be rigid. But what Goldreich and Thal showed in 2013 is something much, much stronger. That is, if you're only thinking about rigidity, you can actually think of random matrices with much more structure. Right? In other words, random Toeplitz matrices have high rigidity with high probability. I need to define what a Toeplitz or Hankel matrix is. So a Toeplitz matrix is one on the left, right? Where along every diagonal, the elements are the same. And the Hankel matrix is one along every anti-diagonal, the elements are the same. These are mirror images of each other. And what Oded Goldreich and Avishai Thal showed is that if you consider a random Toeplitz or Hankel matrix, what does a random Toeplitz or Hankel matrix mean here? To completely specify a Toeplitz matrix, 2n minus 1 elements are enough, right? You can just take 2n minus 1 elements and completely define a Toeplitz matrix because these are only along the diagonals. They're going to be the same. And you say a matrix is a random Toeplitz matrix. Here we are only considering F2. If these 2n minus 1 elements are chosen independently and uniformly at random from F2. So such matrices have rigidity something like n cubed by r square log n for rank r with high probability. That's what they showed, where the rank is within this range. Okay. So one question you might ask is, does this get far to Valiant's question? It's definitely better than what we have from the untouched minor argument for certain values of r. right? Asymptotically better. And there is something more that this actually gives. Right? It's not just that we got slightly mildly asymptotically closer to answering Marlene's question. The best we had was something that was non-explicit with high rigidity. Now we'll have a construction in exponential time given an NP oracle. How do you do this? You can just simply think of running over all Hankel or Toeplitz matrices which have n by n dimension and entries are 0, 1. So here the time taken is something like 2 to the order n as opposed to 2 to the n square, because you just need 2n minus 1 elements to completely specify Toeplitz matrix. And now for each of these matrices, you have to test whether the rigidity has this bound. You definitely know that there exists one from Goldreich-Thal statement. Now we need to search for that. How do you do that? You take this matrix, Toeplitz matrix, and you check whether it can be written as a sum of a matrix of sparsity this much and rank R. Right? For R within this range. If you fix an R within this range and do this. For this, you need to guess a sparse matrix, guess a low rank matrix, and test whether T can be written as S plus N, which can be done in NP over F2. So that's the catch. So it's in exponential time given an oracle to NP. That is slightly better, right? So I'm not sure how much time I have. I was thinking of presenting a proof of this, but I'm going to skip it. But the slides I think will be available. So in case you want to see.
So aren't these tests like the most naive ones that you can think of?
Yeah, yeah.
Like just going through everything.
Exactly. So one way to see this is that's how hard rigidity is. But just wait for 5 more minutes. Just 5 more minutes. And one question that you might ask is, okay, you're telling me it's an NP for finite fields. What can you say about other fields over reals, over, there might be people who are interested in algorithms for computing the rigidity. This will be discussed in Golovnov's talk.
Okay, yeah.
So you may have to wait a bit for the computational complexity of rigidity. Okay, so we have spent nearly 55 minutes. At the end of it, I'm telling you that we can construct matrices in exponential time that have moderate rigidity. One catch here is that you can actually get rid of the NP oracle here. And this you could do by looking slightly into the proof, because this is over finite fields, things like that. You can, just like someone mentioned, you can do a brute force. And you can get rid of this NP oracle. So this gives an exponential time construction. But I'm not going to get into the details. So exponential time construction with moderate rigid matrices is what I'm telling you at the end of 55 minutes. I'm sure like all of you are disappointed, but there is still hope. So 2020 saw tremendous progress in rigidity. Like what is tremendous, I will tell you. But what beyond better constructions, it actually threw light on the way we see rigidity. And these are the results from 2020. The first result is by Mrinal Kumar and Dandy Wok. This is a sub-exponential time construction of rigid matrices. From exponential, we come to sub-exponential, where the rigidity is something like n square by log n for rank that is asymptotically better than root n. Right? And this is for a matrix over F2. I've just written all these results for F2, but they work for any finite field as long as n is quite large. So one thing that is nice about this result is it uses linear circuit lower bounds. We did see that rigidity lower bounds imply linear circuit lower bounds. And I would have expected that somebody asked, is the other way true? Right? If we show linear circuit lower bounds, can we show rigidity lower bounds? And this result is along that direction. The second result is due to Josh Allman and Lee Jie Chen, which is also from 2020. They gave an explicit construction, explicit in the sense a construction in time polynomial given access to an NP oracle, which has quietly high rigidity. That is, you will have to change at least n square entries in the matrix in order to reduce the rank to this much. So one thing you might be less surprised is that you need an NP oracle. So can we get rid of this? And suppose, let's say in 2021, we actually got rid of the NP oracle. Does this answer Valiant's question immediately? The bounds are not as required by Valiant in the sense that this is not super linear. But what makes this result really interesting is that this gives a connection between rigidity and what are called probabilistically checkable proofs. This is a connection we would not have quite expected in general, and this connection makes it really interesting. Another interesting thing about this is, so far I was writing functions of n here, right? Epsilon n or n by 32. Suddenly there is a 2 to the log n to the 1 by 4 minus epsilon, although you can still express this as a function of n. This notion of rigidity was also studied independently by Rasberov, where he looked at slightly larger sized matrices and talked about their rigidity. And these have connections to communication complexity lower bounds. So this result of Allman and Chell actually gives a new lower bound in the setting of communication complexity. So that is one nice thing that we did in 2020. An improvement of this result was obtained shortly by Amay, Bangale, Prahlad Harsha, or Paradise and Avishetal. They improved the parameters from 2 to the log n to the 1 by 4 minus epsilon to something like this. This is something like n to the omega 1 by log n. This is also a construction in polynomial time given an NP oracle. This is via more intelligent constructions of probabilistically checkable proofs. And all these three results work for all finite fields. I've just written it here for it. Right? So we are not going to see details of these results, not just in the interest of time, because there are talks that have been dedicated to these results. This is pretty much the roadmap that we did. We defined a goal. We saw that rigid matrices do exist. We have constructions in polynomial time of moderate rigidity and highly rigid matrices that are non-constructible. And we did see that random Toeplitz matrices give us a construction in exponential time. Now, to get to sub-exponential time or p to the np, we'll have to wait until these two talks are done. And I think Ben's talk will throw some light on this, although the talk is actually about other results. I think, yeah, that is pretty much what I wanted to say. I just skipped the proof of Goldreich-Thal. In case people are interested, I think the slides might be.
Thank you very much, Ramya. Yeah, so we have maybe a few 2-3 minutes. If there are any questions, we can still take them.
So maybe this is a silly question. So suppose you have a matrix over some finite field, and let's say you know that it is not rigid. Is it possible that the certificate for rigidity could involve entries from some extension and so on? Like,
yeah, I've seen a notion like this, but I'm not sure if that answers the question. So such matrices are called maximally rigid matrices. Like even if you allow the entries to be changed from an extension field, you won't be able to reduce the rank.
I see. So the two notions could potentially be different. That is, rigidity over the base field could be a little larger than the rigidity over.
Yes. If the matrix is rigid even over the extension, I think it's called maximally rigid or something. I mean, it's called maximally rigid, but I don't know if there are any results in that direction.
Okay, thank you.
So again, one thing that what do you mean by when you say the matrix is rigid? Is there? I mean, I somehow lost track of it during the talk.
Yeah. So we say a matrix is rigid if it has superlinear rigidity.
Okay. Yeah.
We initially in the beginning of the talk we said if it is far from a low rank matrix, where I did not define far and lower. But after Valiant's question, the parameters that make sense are something like superlinear rigidity for rank omega n. So whenever I say high rigidity, we'll have to change at least n to the 1 plus delta. A matrix is highly rigid or matrix is rigid is the same.
Okay.
A while ago, I saw a lot of raised hands, but then they got unraised. Are there still any questions?
Is there a way to see this?
So since you're in sharing screen, you don't see the.
Maybe I'll just stop.
Right now, there are no raised hands.
Maybe people were clapping, I guess. I don't know.
Yeah. Okay. So then, since we are anyway at this, our time is over. So let's thank Ramya once again, everybody. And we have now a 5-minute break. The 10-minute break has shrunk to 5 minutes, and we have 5 minutes to go and grab your coffee or whatever, and then we start with the next talk.
Yeah, Sasha, can you share your screen in the meantime?
Yeah, can you please make me a co-host? The other me, there is another Sasha who would like to be a host.
Oh, okay. Sure.
I thought you are a co-host right now.
I
I
think
see. I see.
devices. Yeah.
No, there are.
Now both are co-host. Yeah.
Yeah, good. Thank you.
Shall I just stop sharing? So that...
Yes.
Question for the organizers: will the slides be put up on the workshop page?
Yes, they'll be available on the web page. Yes.
Yeah. So the parts from Ramya from your talk that were skipped, people can still go for them. If they don't want to read your survey, at least the slides will be there. Yeah.
Sure.
Should I start?
Yeah, I thought we'll just wait for a minute because I said 5 minutes from the last.
Oh, okay, sure.
Yeah, okay. So maybe now we are ready to start. Yeah. So welcome back from this break. Our next talk now is part 2 of this tutorial introduction to matrix rigidity, and this will be given by Sasha, who is in fact one of the organizers of this workshop also. And as you can see from this title, Sasha Golovnev. But for those who don't know, when you're looking in the papers, look for A Golovnev, not for S Golovnev. Yeah. So Sasha is currently at the Georgetown University in USA. He did his PhD from New York University on circuit complexity. And after that, he has spent time as a postdoc and as a research scientist in various places: Harvard University, Columbia University, Yahoo Research, and yeah. And current interest is one of his current leading interests is in matrix rigidity, and he's going to continue this tutorial now. Sasha, over to you.
Thank you for the introduction, and thank you everyone for staying for this talk. This is the second part of Introduction to Matrix Rigidity, and I highly recommend to watch the previous talk by Ramya, the first part. But for those of you who missed it, I will remind the main definitions and the key results from Ramya's talk. All right, so, and luckily, Ramya defined everything what's going to be needed for later talks, and all the technical stuff is going to be in the later talks. So this talk is going to be quite informal. I'll just give the necessary context for this kind of questions and problems. Also, please do ask questions during the talk. Either just unmute yourself or type your question in the chat. All right, so outline of this talk is the following. First, I'll remind the key definitions, explicit and semi-explicit constructions from Ramya's talk. Then we'll talk about limitations for current techniques for proving rigidity lower bounds. So more or less we'll prove rigidity upper bounds. We'll show for what matrices we cannot prove rigidity lower bounds. And finally, we'll talk about some applications of matrix rigidity, because besides of being a very beautiful question in combinatorics, so at the intersection of maybe algebra and geometry, matrix rigidity also has many cool applications to various areas of theory. All right, so let's start. First, rigidity of a matrix A over a field F with a parameter R is the minimum number of entries you need to change in this matrix A to drop its rank below R. So once again, fix your favorite field F. Now we're considering an n by n matrix A, and its rigidity for the rank parameter R is the minimum number of entries you need to change to drop the rank of A below R. All right. And here is an extremely, so a non-rigid matrix is a matrix that can be written as a sparse plus low rank matrices. And a rigid matrix, a hard matrix, a matrix that we want to find, is a matrix that cannot be written as a sum of sparse and low rank matrices. All right. And here is an extremely simple but very elegant example due to Midrijani's 2005. So I'm defining an n by n matrix M, which is just a bunch of identity matrices stacked together. Each identity matrix is of size 2R by 2R. So in my n by n matrix, I have n over 2R squared identity matrices. Right? So what the rigidity of this matrix M for the rank parameter R? If you want to drop its rank below R, you got to drop the rank of every identity matrix below R. Every identity matrix of size 2R has rank 2R. So if you want to decrease its rank to R, you got to make at least R changes. In every copy of identity, you have to make at least R changes, and the number of identities is n squared over 4R squared. So you have rigidity at least n squared or n squared over R. All right. So that's a very simple, very explicit matrix with rigidity n squared over R. And we can construct such a matrix for every R. So here I assume that n is a multiple of 2R, but clearly if it's not, I can do something similar, right? Okay, so the current state of the art is the following. For circuit lower bounds, we need superlinear rigidity for linear rank. As Ramya showed in her talk, if you get a matrix that for some linear rank has superlinear rigidity, then you get a superlinear circuit lower bound and resolve a big open question in complexity. And in fact, for some circuit lower bound, it's sufficient to get any superlinear lower bound. It will be a superlinear lower bound on some restricted class of circuits. It will still be a very big result in circuit complexity. So we just need to get any superlinear rigidity for linear rank. Okay, and in this trivial, very simple example, we saw how to construct a matrix of rigidity n squared over R. In particular, when R is linear, then we get linear rigidity. Right? This trivial example for linear rank gives you linear rigidity. So literally any asymptotic improvement on this trivial example would resolve a big question in circuit complexity. We need any improvement on this trivial example. But despite much effort, in this 45 years, the best known explicit lower bound is better than the trivial bound only by this log n over R factor. And the funny thing is that for this interesting regime where R is linear, this log factor doesn't even matter. It's just some constant. So for this regime, we essentially know nothing better than the trivial example we saw on the previous slide. All right, so what do we mean by explicit here? As Rami mentioned, we just mean a polynomial time algorithm that outputs, say, decimal or binary representation of every entry of the matrix. So if we have a polynomial time algorithm, we get a good circuit lower bound. But in fact, we don't even know circuit lower bound, non-trivial circuit lower bounds for a much larger class, not for the class of polynomial time algorithms, but even for the class of algorithms that run in time 2 to the order of n. This class is called E, and just algorithms that run in deterministic time 2 to the order of n. If you construct a rigid matrix in this class, that is, if you have an exponential time 2 to the order of n time algorithm that outputs a rigid matrix, that will still be an interesting circuit lower bound. Moreover, even for a larger class, e to the np, that is a class where you have exponential time, and also whenever you see a problem from np, say np complete problem, maybe even of exponential size, you can solve it just in time 1. So I'm giving you this power. First of all, you have exponential time. Second, you solve even huge NP hard problems in just time 1. Use this power to output an to output a rigid matrix. If you could do this, we would get a circuit lower bound for this class. And this would also resolve a big question in complexity. We don't know any non-trivial circuit lower bound for this huge class. So a rigid matrix, even in e to the np, would be a big deal. Okay, so let's call constructions of rigid matrices that use this maybe exponential time or np oracles or more randomness or some, I don't know, other things like algebraic independence. So let's call such constructions semi-explicit. They're not polynomial time, but they're still much better than a random matrix. So what do we know about? Yeah. Yes.
Can you mention what do you mean by new circuit lower bound for this rigidity, this omega n? Like anything? This is not the variance result, right? I mean, it is something because
this is also variance result. This will be just for restricted class of circuits that are called series parallel circuits. So the thing here is the following: you can define a class of circuits that's a restricted class of circuits. Here, essentially, all what you do is you precompute something, then combine the results, compute like the results based on the previous computations. I mean, there is a formal definition, but just all the edges go like either in series or in parallel. any superlinear rigidity lower bound would prove a superlinear circuit lower bound for the series parallel class of circuits. And this class of circuits is interesting because all our circuit upper bounds are series parallel. That's how like people come up with circuits. We say, if I want to solve a problem by a circuit, I'll solve a bunch of smaller problems, combine their results. Solve a bunch of smaller problems, combine their results. So all our upper bounds are series parallel. So the first question is to prove lower bounds at least for this class of circuits.
Okay, yeah, sounds good.
Yeah, even in e to the np. All right, so let's call constructions of rigid matrices that use maybe exponential time, NP oracles, randomness, or anything else, semi-explicit. And here's what we know about semi-explicit constructions of matrix rigidity. So let me remind you that the best explicit construction has rigidity n square over r times log of n over r, and we can output it in polynomial time. Ramia explained in her talk that a random matrix has maximal rigidity, has quadratic rigidity, in fact, over any field. And we can brute force it in super exponential time, in time 2 to the n square. We can brute force essentially all matrices and construct extremely rigid matrices. They're even more rigid than we need for circuit lower bounds. We don't really need n square rigidity, but that's what we find. The only bad thing about this construction is that it uses too much time. It uses time 2 to the n square, and interesting construction would only use time 2 to the order of n. Okay, so the first construction is not sufficient for circuit lower bounds because its rigidity is low. This construction is not good because it uses too much runtime. In fact, we can brute force only sparse matrices and still get rigidity sufficient for circuit lower bounds. But even brute forcing sparse matrices still takes super exponential time. All right, we can brute force fewer matrices in sub-exponential time, which is good, which is less, which is like in E, but here we only get rigidity for rank say square root of n, which is not sufficient for circuit lower bounds. Also, we can use some algebraically independent entries or linearly independent entries and construct very rigid matrices. But the problem with these constructions is that we can't output decimal representations of those entries. So they have like infinitely many digits. And for this kind of constructions, please watch Ben Lee's talk tomorrow. He'll give constructions of similar flavor. And yeah, and those results are extremely interesting, I think. Another semi-explicit construction that Ramia sketched in her talk was rigidity of Henkel matrices, or Toeplitz matrices, or circulant matrices. They are much more rigid than what we know explicitly, and we can actually brute force them in time 2 to the n and check their rigidity in time 2 to the n, which is good for circuit lower bounds. But unfortunately, for linear rank, they don't have enough rigidity. They don't imply circuit lower bounds either. And finally, a recent line of breakthrough works gives a construction in P to the NP, which is amazing, which is much better than E to the NP, that has maximal rigidity, quadratic rigidity, but for slightly subpolynomial rank. The rank parameter is not large enough to imply circuit lower bounds. And I will present these constructions tomorrow. Let's watch his talk tomorrow too. All right, so this is what is known in terms of semi-explicit constructions of rigid matrices. We know many beautiful constructions, many beautiful recent constructions, but none of them is yet sufficient for circuit lower bounds. But clearly we're getting closer and closer. All right, any questions so far? Then now we'll talk about limitations. So where do we get rigidity? Where do we get rigid matrices? In theory, we anyway study many matrices, and Satya in his book 10 years ago said, okay, let's since we anyway study many matrices, let's check which of them are rigid. One may conjecture that many of the matrices that we study are rigid because we don't really know for them a simple, natural, closed form way to represent them as a sum of low rank and sparse matrices. Hence, one may conjecture that maybe they're rigid. So Satya suggested let's study them. Either we find one of them which is rigid, which is amazing, we get circuit lower bound, resolve a long-standing open problem, or at least we learn a great deal about these important matrices. And a spoiler, unfortunately, we have learned a great deal about these matrices. All right, so here are the candidate matrices, say Walsh-Hadamard matrix or other kinds of Hadamard matrices. Discrete Fourier transform matrix or other Vandermonde matrices, maybe Cauchy matrices, matrices that have many full rank submatrices, generator matrices of linear codes, Hankel-Topless matrices, projective planes, other Cayley graphs. So we have many matrices that we study, and for none of them we knew non-rigid decomposition. All right, so let's look at some of them. Let's take a closer look at some of them. Let me remind you an untouched minor proof that Ramya presented in her talk. So untouched minor is a method of proving rigidity lower bounds, and it works in two steps. First, you say that first we just prove that if you change only n squared over r times log of n over r entries in an n by n matrix, there is still some r by r submatrix which is not touched. Okay, so we prove it, and Ramya sketched the proof in her talk. And now, after we prove this, all what we need to do is just to take any matrix, just present any matrix such that all of its r by r submatrices have full rank. Right? Since now, if you change only n squared over r times log entries, there is an r by r untouched matrix, and this matrix must be full rank. Hence, you have some rigidity. That's a nice method of proving rigidity lower bounds. It's essentially best known explicit lower bound, and one may hope that we can improve this lower bound in this method. For example, because the combinatorial result that we use in the first step, it is not known to be tight for many settings of parameters. But unfortunately, it is tight for our setting of parameters. So, for example, yeah, we can actually say that this method can only prove this rigidity lower bounds and nothing better. For example, there is an explicit set of n squared over r times log of n over r entries in an n by n matrix, such that those entries touch every r by r submatrix. Even a random subset of that many elements of the matrix would do the job with high probability, but you can actually de-randomize it. So there is a very explicit set of that many entries that touch every r by r submatrix. So this argument won't prove stronger rigidity lower bounds, but in fact there is another limitation for this method. There is a matrix where not only r by r submatrices have full rank, but all submatrices have full rank. And yet its rigidity is exactly n squared over r times log of n over r. So this approach cannot prove anything better. It can prove this lower bound, but nothing better. There are matrices whose all submatrices have full rank, but they are not rigid. Any questions? Okay, so such matrices called superregular matrices, and now we know that there is no way to prove that all superregular matrices are rigid. Okay, let's look at, say, linear codes, a generator matrices of linear codes. Let me remind you what a linear code is. A linear code is just the k-dimensional subspace of the n-dimensional vector space. Okay? And the distance of this code is the minimum sparsity of a non-zero vector in the subspace. The minimum number of non-zero entries in a non-zero vector from the subspace. Okay, and a generator matrix is any basis. Say it's a matrix whose columns generate the subspace. Since there are many bases for every non-trivial subspace, there are many different generator matrices for every code as well. Okay, there exist codes with kind of optimal, ideal parameters. Namely, there are codes over any field such that their dimension is linear in n, but their distance is also linear in n. That is, a sparsity of any non-zero vector in the space is at least linear in n. I mean, is linear in n. Okay. And such codes where both of these parameters are linear in n and the ambient dimension are called good codes, good linear codes. All right. So we know 3 ways to prove that every generator matrix, essentially every generator matrix of a good code is rigid, is n squared over r times log of n over r rigid. And in fact, it's easy to show that every good code has a generator matrix of maximal rigidity, of quadratic rigidity. We don't even need that much rigidity for circuit lower bound. So once again, there are many bases for subspace, so there are many generator matrices. And for every code, there are generator matrices which are very rigid. We just don't know how to find them. And in fact, in 2016, David Weir showed that some good codes, at least some good codes, have generator matrices that are only that rigid, only n squared over r times log of n over r rigid. So our previous rigidity lower bounds worked for every generator matrix of a good code. And this result says that actually you cannot improve this result for every generator matrix. There are generator matrices that are only that rigid. So that's another limitation. It says that there is no argument that says that good linear code, every generator matrix of a good linear code is rigid. Any questions? Good, but still, until 2017, we had been living a dream. We had so many, we had so many candidates. Just pick one and prove that it's rigid. But then a series of works, unfortunately, proved that most of these matrices are not rigid. So let's take a look at the Hadamard matrix. It's maybe like the most well-studied matrix in theory. So the 2x2 Hadamard matrix is just a matrix with entries 1, 1, 1, minus 1. And larger Hadamard matrices are just a bunch of copies of H2 stacked together, just like negated every once in a while. So here's a formal definition. Every larger Hadamard matrix is just 4 copies of smaller Hadamard matrices, one of which is negated. And for a long time, we believed that this Hadamard matrix must be rigid. And there is a long line of beautiful works showing stronger and stronger rigidity lower bounds for various Hadamard matrices. It started with a lower bound of n squared over r to the 4, and ended with this currently best known rigidity lower bound for Hadamard, which is n squared over 4r. And then in 2017, Josh Allman and Ryan Williams say, okay, those are indeed very beautiful lower bounds, but they're not going to lead to a circuit lower bound. The Hadamard matrix is not rigid for linear rank. Hadamard matrix is not sufficient for proving circuit lower bounds, whereas this matrix rigidity approach. Okay, so please watch Josh's talk tomorrow, where he'll give a new recent proof of this fact. Okay, so now we know that Walsh-Hadamard is not rigid either. Then David Weir and Ben Edelman extended this approach and proved that some other natural class of matrices is not rigid either. And finally, last year, David Weir and Alan Liu extended this result to prove that many other candidates are not rigid. For example, they showed that the discrete Fourier transform matrix is not rigid enough for circuit lower bounds. Then they said that Henkel matrices are not rigid, then projective planes, then Cayley graphs. So we have only a few candidate matrices left now. And this is a state of the art of this limitation results in matrix rigidity. Please watch George's talk tomorrow, where he will sketch many of these proofs. All right. This is what we know about rigidity upper bounds, and now let's switch to applications of matrix rigidity. So we found applications of matrix rigidity to several areas: to communication complexity, circuit complexity, data structure, lower bounds, error correction codes, and we will see some of this. Let's look at some of these applications. So the earliest one was by Razborov in 1989. He said that if you find a matrix, explicit matrix, which has non-trivial rigidity even for sublinear rank, then you resolve a long-standing open question in communication complexity. Namely, you find a language that does not belong to polynomial hierarchy in communication complexity. Big question in communication complexity. So here he says just find a non-trivial rigidity for sublinear rank. You don't even need a linear rank here. But unfortunately, our explicit lower bounds are not rigid enough for this result. But the most recent semi-explicit construction of rigidity that uses PCPs is actually rigid enough for this theorem. The rigidity lower bound that I will present tomorrow is sufficient for Razborov's theorem. In particular, it implies that e to the np does not belong to a polynomial hierarchy in communication complexity. They even prove this result for a smaller class than e to the np, say for the class where running time is just maybe 2 to the log n squared plus an np oracle. Even this class does not belong to communication complexity polynomial hierarchy. So this is not yet completely explicit. This is not P, but yeah, we're getting there. All right, so this is the known application of matrix rigidity to communication complexity. Now let's talk about circuits and rigidity. So let me remind you one of the circuit models that is relevant to matrix rigidity. So we say a Boolean circuit computes a function from, say, n inputs to n outputs if it computes it by a straight line program. That is, you have this program with no branchings, with no if statements, no loops. You just run it like one line after another. Okay, you can always write a straight line program as a directed acyclic graph, and such a graph is called a circuit. And here, if we talk about Boolean circuits, then we have n inputs and Boolean inputs. We have this constants 0 and 1, and gates compute, say, any binary functions, any functions of 2 Boolean inputs, and we do not pose any restrictions on the out degree of this gates. Okay, this is a Boolean circuit model. So what is known about this model? In the 40s, Shannon proved that almost all functions require circuits of size 2 to the n. And then in the 50s, Lupanov gave a matching, essentially matching upper bound. All functions can be computed by circuits of size 2 to the n. So we know that almost all functions have exponential circuit complexity. And again, as always, the challenge is to find an explicit function that is hard. For example, if we want to prove that p is not equal to np, it's sufficient to find an explicit function that cannot be computed just by polynomial size circuits. We don't even need exponential lower bound, just super polynomial lower bound for a function from np. That would separate p from np. Okay? So we know that most of the functions have exponential complexity. We only need super polynomial lower bound, and the best what we can prove is roughly 3n. So even for a function from e to the np. So clearly when I improve on this 3n lower bound, and we have many candidates for super linear circuit lower bounds. There are many functions that we believe should probably require circuits of super linear size. Say we know how to multiply 2 integers by a circuit of size n log n. And one may conjecture that this is optimal, that we should be able to prove the matching lower bound. We just don't have necessary tools yet. Or say the discrete Fourier transform. We also know how to do it by a circuit of size n log n, but we just don't know, we don't have tools of proving matching lower bound. And there are many other simple and natural problems, say various shifts of the inputs, permutations of the inputs that we know how to do in time n log n by circuits of size n log n, and we conjecture that they require circuits of size n log n. We just don't know how to prove these lower bounds. Or perhaps you can take your favorite NP-hard problem. Perhaps it requires superlinear size circuits too. Okay, so we have really many candidates for superlinear circuit lower bounds. We just don't have tools to prove such lower bounds. What do we do when we can't prove lower bounds for a computational model? We usually consider like restricted version of this model. And for the model of circuits, one natural restricted model is to look at the depths, is to bound the depths of a circuit. Depth is just the longest path from an input to output. It's a natural parameter that we want to bound. So if we consider circuits of depth 2, those are essentially CNFs and DNFs. And this is the only circuit model that we understand quite well. And here we know optimal circuit lower bounds. We know that even the parity function requires circuits of size 2 to the n. But when the depth is 3 or some other constant, we still know exponential lower bounds. When depth is, say, 1.9 log n, and your circuits have Fannin 2, they are bounded Fannin circuits, then we know functions that cannot be computed by such circuits. We still have lower bounds. But already for depth 2 log n, we know nothing better than this almost trivial lower bound of 3n. Hence, a natural question, this main question on the frontier is prove any non-trivial lower bound, say 10n lower bound for circuits of logarithmic depth, maybe 10 log n depth. Or better yet, prove a superlinear lower bound for log depth circuits. So this is a problem on the frontier. We want to prove superlinear lower bounds for log depth circuits, because that's the easiest problem that we don't know how to solve. And Unlike the case of unbounded depth circuits, where we just don't even have tools for proving superlinear lower bounds, here Valiant in the 70s gave us a nice tool that can potentially lead to superlinear lower bounds for this log depth circuits. And a similar question on the frontier is the same one, but for linear circuits. For circuits where every gate computes a linear combination of the inputs. Again, we know how to prove a lower bound of 3n, but we want to prove a superlinear lower bound, at least for log depth circuits. When every gate computes a linear operation of the previous gates. Say O of 2 for Boolean circuits, every gate is just XOR. Can you find an explicit function from n inputs to n outputs where such that every circuit where all gates are just XORs and the depth is logarithmic must be of superlinear size? That's another question, another problem on the frontier. And formally, it's incomparable to the previous question, where like not linear but general circuits. Because here we have weaker computational models. We have only XOR gates essentially, but also we can only consider linear problems, right? Linear circuits can only compute linear problems, so it's not fair to prove lower bounds against non-linear problems. We have fewer problems to prove lower bounds for, but we're proving lower bounds against a weaker class of circuits. So formally, this problem is incomparable to the previous one, but it feels like it should be easier because this is kind of linear algebra question, and we tend to think that we understand linear algebra. Okay, so this is another problem on the frontier. And Valiant in the 70s said that if you find a matrix that has superlinear rigidity for linear rank, then you resolve this question. Then you get a function, the corresponding function cannot be computed by a log depth linear size circuit. And the way he proved it, Rami showed the proof. You can another way to view Valiant's proof is the following. He says he applies depth reduction. He says that if you have a log depth circuit of linear size, you can reduce the depth to just 2. If a function can be computed by a linear size log depth circuit, it can also be computed by the following depth to circuit. You have n inputs. You preprocess them by any functions. You preprocess them by very complicated circuit to epsilon n bits. So in this preprocessing stage, you lose some information. You go from n bits to epsilon n bits. But now you can efficiently compute every output. Clearly, I cannot say that every output is a function of this preprocessed data, right? You lost information in the preprocessing stage. This I cannot say. But luckily, I can say that, as Valiant said, that every output can be computed by looking at only few memory cells, these preprocessed memory cells, and a few inputs, only some n to the delta of them. So another way to state Valiant result is the following. If you have linear size log depth circuit, it can also be computed by this simple depth to circuit, where you preprocess input into epsilon n bits and then compute every output by looking at only n to the delta preprocessed bits and n to the delta inputs. If you find a function that cannot be computed by this depth to circuit, superlinear circuit lower bound. Okay. So if you get a matrix which is rigid for rank, say n over 100 and sparsity n to the 1.01, then you get superlinear log depth circuit lower bound. This balanced depth reduction is purely graph theoretic. He only looks at the graph of the circuit. He views the circuit as a graph and never looks at what is computed at the gates of the circuit. And it is known that this approach can only work for log depth circuits. There is no graph theoretic depth reduction for unbounded depth circuits. But if you look at not only at the structure of this graph of the circuit, but if you also look at what is computed at the gates of the circuit, then apparently you can do depth reduction for unbounded depth circuits, but unfortunately only for small size circuits, only for circuits of size 4n. So a recent result shows that if you get just linear rigidity, not superlinear, but linear rigidity for high linear rank, then you'll get some lower bound for some linear lower bound, not superlinear, but just linear lower bound, but for unbounded depth circuits. It is better than valiant results in that it proves lower bounds against unbounded depth circuits, but unfortunately, it can only prove very weak circuit lower bounds. So in other words, if you find a matrix that is rigid against very large rank, but very low sparsity, you get a new circuit lower bound for unbounded depth. It says that if you change all the parameters of Valiant's result to the opposite, the theorem still holds. If you get for high linear rank, low sparsity, you get small circuit lower bound, but for unbounded depth. Every single parameter is the opposite to what Valiant had.
Yeah, just to recheck. So this lower bound will be for linear circuits, right? Not for Boolean circuits.
Right. For linear Boolean circuits. Oh, for linear circuits over any field, in fact.
Yeah. So for linear circuits, what is the best known lower bound? For Boolean, it is 3 plus 1 by whatever. And
yeah. So yeah, that's a very good question. So here is what's best known for, say, general Boolean circuits. That is, you can use non-linear gates. If you only use and or a negation, then we can prove a lower bound of 5n minus little of n. If you use all binary gates, that is, you use and or negation, XOR, equality, and things like this, then it's slightly better than 3n. It's like 3.01n. For linear Boolean circuits, here it's important to understand that when we're talking about linear circuits, then we never consider, so here I'm talking functions from n bits to even just 1 bit. If we're considering circuits from n bits to n bits, then you can just always add n to the lower bound. For this, we know lower bounds 6n and 4.01n. Okay. For linear circuits, we never consider one output. Why? Because every linear combination of n inputs can be trivially computed by a full binary tree, so of size like n-1 and log depth. One linear function can always be computed by a circuit of size n. So for linear functions, for linear circuits, we always consider n inputs, n outputs. And here, the best known lower bound is 3n minus little of n. Yeah, in fact, if you consider just log n outputs, you still get essentially the same 2n, yeah. All right, that's the best known lower bounds. And here is one potential way to prove a lower bound of 4n. For this, we need to find a matrix that is rigid for high linear rank, but very low sparsity. We still don't know explicit constructions of such matrices. All right, there are other beautiful connections between rigidity and circuit lower bounds. say Josh Allman and Ryan Williams show the connection between rigidity and the class of circuits where you have AC0 gates, some mod P gates, and some threshold gates. But I won't sketch this connection in this talk. All right. But this depth reductions results actually bring us to a connection between data structures, static data structure lower bounds, and rigidity lower bounds. For more on this, please watch Siva's talk right after this talk today. Let me just give some introduction. So we all know many data structures, and the classical ones include lists, heaps, all kinds of search trees, all kinds of hashes, Blum filters. But here we consider more sophisticated data structure problems. And one example would be graph distances, right? So in the graph distance problem, I'm giving you a road network, say all roads in the US. And I can assume that probably this network is not gonna change in the next 2 weeks. So I have 2 weeks to preprocess it, which is essentially unbounded amount of time to preprocess this network. But once I'm done preprocessing, I want to quickly find shortest path between say pairs of cities. So I'm giving you a road network, and I assume it's never going to be changed. You have a lot of time to preprocess it. But once the preprocessing is done, please quickly answer my queries. Say what's the shortest path from here to there, and that's more or less what Google Maps does, right? Or another example would be nearest neighbors. Here, I'm giving you, say, cluster centers, some points on the plane maybe, cluster centers. Again, you have unbounded resources, unbounded time to preprocess them, but once you're done preprocessing, I'm giving you a query point, find which cluster it belongs to, find the closest point or one of the closest points. And I want this query stage to be very efficient. And that's what Netflix does for recommendations, or many other machine learning algorithms do for recommendation systems. Or another example would be range counts. And again, I'm giving you a bunch of points, say on the plane. You preprocess them, again, in bounded time. Once you're done, my queries are, here is a rectangle or maybe high dimensional box. How many points are there in this box? Or maybe how many, approximately how many points are there in this box? And that's what some companies say Amazon use for market size estimation of certain segments. All right, so these data structure problems are called static data structure problems because here we assume that the input is not going to be changed. It's static. I'm giving you input. It's not going to be changed, preprocess it. But then I want you to make the query phase efficient. So in the case of this graph distances problem, I'm giving you a road network. You preprocess them into a bunch of zeros and ones. But then once I'm giving you a query, quickly find the shortest path between like a pair of cities. Just look at the very few positions in your data structure and find the shortest path. I'm giving you another query. Again, you're looking only at the very few positions in your data structure, and you find the shortest path. Okay? And formally, a data structure is the following thing. You have a static data structure. You have n input, say, from your favorite field. You preprocess them using unbounded resources into some S memory cells. And then every query spends only time t. In particular, it looks only at t memory cells and computes an answer. So here you have m queries, and the queries are known in advance, right? You know all possible pairs of cities in the country and the world. You know them in advance. So all queries are already known to you. You just need to find an efficient way to preprocess the input such that later you can efficiently answer all queries. And we typically, and we usually say that a data structure is efficient if the space is nearly linear, say n times polylog n. And the query time is reasonable, maybe polylog n or n to a small constant epsilon. Okay, that's what efficient data structures are. Okay, this is what data structures are, but let me also remind you Whelan's depth reduction result. He says this is what efficient circuits are. Every efficient circuit can be computed by this depth to circuit or this kind of data structure. The difference between the two is that in the setting of data structures, you take n inputs, you preprocess them into more than s memory cells, and then efficiently answer every query by looking only at memory cells. In the case of circuits, you preprocess the inputs into fewer than n memory cells, but then answer each query by looking at a few memory cells and inputs. So this is the difference between two settings. And we'd really love to say that these two pictures are equivalent in some way. The data structures are same things as circuits. That would be amazing. We don't know how to do this. Yeah. What we do know how to do is to say that we can actually prove that these two pictures are essentially equivalent when the problems are linear, data structures are linear, and circuits are linear. So for a linear circuit, we compute for an input x, we compute matrix times x, right? Some matrix m times x. That's what a linear function is. That's what a linear circuit computes. And by Whelan's depth reduction, every small circuit can be computed by this depth to circuit. But also when everything here is a linear function, this means that you can write this matrix M that your circuit computes as the following sum. First, in the matrix A, I will write dependence of outputs on inputs. Here I just described how every output depends on all the inputs. That's some matrix A, some linear transformation, some matrix. And then in matrix C, I'll write how every output depends on memory cells. And then in matrix D, I'll write how every memory cell depends on the input. Okay, but recall that every output looks only at a few inputs and memory cells. So these two matrices, A and C, are sparse. Every row in them looks only at a few memory cells and few inputs. So they're sparse. And look here also, the middle dimension of these two matrices is somewhat small. It's just epsilon n. So this means that my matrix can be written as a sparse plus low rank, right? The product of two matrices with low middle dimension is low rank matrix, of rank at most epsilon n. So this is exactly Whelan's result. It says that small circuit can be computed as a sparse plus low rank, that is a non-rigid matrix. Okay, so for the case of linear circuits, this decomposition exactly corresponds to non-rigid matrices. And for linear data structures, we can do the same thing. What is a linear data structure? Now, everything computed in this layer is linear. Everything computed in this layer is linear. So I can write the matrix that I compute M as a product of two matrices. One encodes the dimension, the dependence of outputs on memory cells, and the other matrix encodes the dependence of memory cells on the inputs. So there is for linear problem M, for linear matrix, for matrix M, there is an efficient linear data structure if and only if it can be factorized as such a product, A times B. And here again, A is sparse matrix, the dependence of outputs on memory cells, and B is actually kind of small matrix. Look, so in data structure, you may have, say, I don't know, some polynomial number of queries. M, the number of outputs, the number of queries, the number of pairs of cities is like n to the n squared or n to the 10 or n to the 100, some huge polynomial in n. So this matrix M is of size n, I don't know, to the 10 by n, n to the 100 by n. And this matrix B is just of size the amount of space your data structure use by n. And the amount of space might be like n log n and polylog n by n. So this matrix is really tiny if you compare it to this matrix. So an efficient data, there is an efficient linear data structure if and only if your matrix can be factorized as a sparse times small. And now we can compare data structures to circuits again, linear data structures to linear circuits. Matrix M has a small linear circuit if and only if it can be written as a sum of sparse plus low rank, if it has non-rigid decomposition. And matrix M has an efficient linear data structure if and only if it can be factorized as sparse times small. And for these two decompositions, we can actually prove that they're essentially equivalent. So for this, for linear data structures and for linear circuits, we can say that they're essentially equivalent. Lower bounds in one model would imply lower bounds in the other one, and so on. And please watch Siva's talk later today for proofs of these results. Okay, I'm going to end here. I just wanted to say then that I'm looking for PhD students at Georgetown. And if you're interested, please drop me an email. That's it. Thank you for your attention.
Thank you very much, Sasha. This is a really nice talk. We still have a few minutes for questions if there are any at this stage.
I'd like to ask a question.
Yeah, go ahead.
So for the last part, like, is one of them trivial? I mean, is one of them easier direction in the case of like the general connection between data structures and circuits? Like, for example, this naive idea that if you have this, if for example your S is like n log n, right? Then I could just consider the problem of like copying the input itself, and then just say that it depends on just the, like if I have a small like a depth reduction for circuits.
Right. This connection. Right. No, that's a very good point. This connection is indeed trivial, but for some setting of parameters. So both of these problems have two parameters, right? We want to trade off two parameters. Say for data structures, we want simultaneously optimize space and query time. And for rigidity, we also want to simultaneously optimize rank and sparsity. So indeed, for some parameters, when data structure space complexity is super linear, then this connection would is indeed trivial. Yeah, but in fact, as Siva will show, that these two decompositions are almost equivalent for all settings of parameters.
Thank you.
Yep. Other questions?
Okay, I don't see any other raised hands or anything either. So, yeah. So maybe we close this talk now. Thanks, Sasha, once again. And we now have a 10-minute break. We'll start again at so it is 10:10 Indian time here now. We'll start at 10:20. Yeah.
At 10:10, right?
We will start at 10:20.
Oh.
It's 10:10 now. Yeah. So we take a 10-minute break.
Mm-hmm. Can you
So
start?
maybe we could check that Shiva's screen share is working. Would you like to try that out now?
Just give me a second. I'll go ahead and share it.
Okay.
Okay. Yes, we see your screen. Yeah.
And also maybe I'll try the play mode as well, so that to make sure it's like it goes through.
Yeah. So we've.
Is that like
Yeah. Yeah. So we are seeing the next 2-3 slides and then going back. Yeah. Yeah.
Perfect. Yeah. Great. Thank you. Yeah.
Okay. Yeah. So I'll be back in 5 minutes.
Hey Shiva, can you hear me? Mrinal
Yeah.
here.
Yeah. Hello.
Hey, hi, how are things?
Good. How are you?
Good, good. Yeah. Thanks for agreeing to give the talk.
Yeah, no problem. Yeah. I'm very excited.
So you've been in the US all along through the pandemic and everything?
Oh yeah, yeah. Unfortunately, I
maybe
couldn't
I'll just interject and say that currently this is still on live stream. Huh? So in case you want to talk about some controversial things.
Okay.
Oh, thank you. Yes.
Yes.
Yeah, I really want to be back home, especially to see my parents. And yeah, it's a mess.
Yeah. When was the last time you were back? About a year, nearly.
With 2 years actually.
I said 2 years.
Yeah.
Oh, I see. Oh, that's tough. Yeah. Yeah, maybe you wait for a few more months, and with the vaccine, maybe it's safer to try.
Right. Yeah. Yeah, I'm hoping they'll ease things out.
Right. Yeah, travel is still feasible, right? Between India and the US, I know a couple of people.
Right. But what I've heard is I think you have to go through some only Air India type flights. Apparently, not all airlines are doing it now.
Yeah, United, I think, is also doing it. Maybe.
Oh, I see. Okay.
Amay is around. I don't know how Amay travel, and Amay would know.
I see.
Amay is in India currently. Yeah, but it's not. It's probably not completely trivial. All right, Shiva. So I'll catch you in a bit. I'll be back.
Yeah, that sounds good.
Like 5 minutes. Okay. So
yeah, perfect. Yeah, great.
So Shiva, I have an idle question.
Yeah.
I followed the link from your homepage to this theorem LP, but there it does not have LP. It only says theorem.
Right. Yeah, I think it's a limited partnership or something. It's it's
the way we write INC or something like that, is it?
I think so. Yes, exactly.
Yeah. Oh, I see. So I actually thought LP was the CS meaning of linear programming, and then I was wondering what was the connection. I see. Okay.
Yeah.
Limited partnership.
I think so too.
Oh, I should have probably mentioned at the end of the last talk that in these breaks, so the GatherTown site is open, and for socializing, one could also head over to GatherTown. Even after this, maybe after this talk, some people may want to head out there. Okay, so I think it is now 10:20, no? So actually, people have not. I mean, when people physically leave and come back, you can see whether most people are back. Whereas here, it's difficult to see. Yeah, but anyway, it is time. So I think let's go ahead and get started. So welcome back to the third talk of the day of this workshop. The speaker is Sivaram Krishnan Ramamurthy. That's quite a mouthful. So let's just stick to Shiva. So Shiva is currently working at the Theorem LP or Theorem. Before that, he did his PhD at sorry, he did his PhD at Washington, Seattle, with working with Anup Rao, and basically he was looking at questions to do with communication complexity, data structures, depth to threshold circuits. Even before that, he was in Chennai, and he did his studied in the campus next door to where I am. So I do have some connect to him as well. Today, Shiva is going to tell us about matrix rigidity and linear data structures. Yeah. Over to you.
Yeah. Hopefully you can hear me. And yeah, thank you so much. And yeah, really excited to give this talk. And yeah, as Meena said, this is mostly the work I did during my PhD here at University of Washington. And yeah, so let me start the talk by quickly describing some very recent works, and maybe from a year ago, that showed some connections between data structures and circuits. So you can roughly think of like these connections going in like different paths. One, maybe three paths here that you see. One is by looking at data structure problems that like compute inner product queries and showing connections between data structures and rigidity, and then going to circuits via Valiant's original paper. And this was started by like this very nice work of Golovnov and Weinstein, where they showed how linear data structure lower bounds actually imply new rigidity lower bounds. And then there was a follow-up work of mine with like Cyrus Rastian. Also, we did something similar along this line, which I'll explain more in this talk. Another direction was taken by Viola, where he looked at polynomial evaluations and then showed a direct connection between data structures and circuit lower bounds. And this was more in the space of like the data structure space being very large. And there's also another connection through cryptography, where Carrigan, Gibbs, and Kogan used like function inversion to connect data structures to Valiant's common bits model, which again takes you back to circuits. Okay. So in this talk, I'm only going to concentrate on the top left corner of the connection between like data structures or linear data structures and rigidity. Okay. And so the rough outline of the talk is I'll like formally define linear data structures and then talk about a notion called rectangular rigidity due to Alan, Panigrahi, and Yakanin. And then I'll discuss this main result of like DGW, which shows the connection between linear data structures and rigidity lower bounds. And then after that, I'll like talk about another restricted type of data structures called systematic linear data structures, and then show that they're actually equivalent to the notion of rectangular rigidity. And then I'll conclude with like a lower bound for like a rigidity lower bound for the vector matrix vector problem. Okay, and the plan is actually I intend to be simple in the sense that I'll provide almost complete proofs. So and also please stop me with questions if something is unclear or like and yeah, or if something is incorrect or like you have comments in between as I present proofs. Okay, there are probably multiple ways to like arrive at these results. So like yeah, so okay, so let me start. So the main goal of at least data structures is that you actually have some data that you'd like to store and would like to compute some functions of the data in an efficient manner. Okay, so in this talk, I'm going to restrict myself to linear data structures. So I'm going to think of the input data x that's going to come from f2 to the n. It's an n length vector. And you are expected to compute queries of the form, which is the inner product of q with x, where q comes from some predefined set capital Q. Okay, and usually the small q is referred to as the query, and x is the input, and the capital Q is the query set. Okay, and given this, how do you store the data and how do you make the queries? It's in the following way. So you get to store two and inner products. Okay, and you can choose these A1 through A2n. And for every time you get a query Q, you can access a subset of these inner products you have stored, and you would like to output the query inner product of Q times X. Okay, so hopefully this setting is clear. And I would have to say that in a general data structure, you can actually have arbitrary queries, arbitrary data, and like an arbitrary function that you store. It doesn't have to be linear, and you don't have to work with fields of any sort. And one example, as like Sasha mentioned in the previous talk, was that like your input can be a graph, and your query can correspond to finding shortest path distance between like pairs of vertices. Okay, and also I need to like, my bad. So the field can be arbitrary. I'm sticking to F2 because it's simple to think of, and also the space is not necessarily just storing 2n bits. You can store arbitrarily many bits, but I'm just going to stick to 2n. It's not going to change anything in the talk, and hopefully, yeah, good. So let's look at like in this model, two simple. Okay, one more thing that I probably missed to mention was that like when you compute the query, all you care about, there are two parameters that we care about: the number of bits you store, which I've said is think of 2 as 2n. And the other parameter that you care about here is the query time, which is the number of accesses that you make on any query. Okay, so once you read some subset of these stored bits, then you're done. Like we don't count or care about the computation time that it takes to go from there to your actual output. Okay. So hopefully that's okay. And yeah, so some two simple data structures that we can think of for any query set is by just storing all the answers you need. Inner product of the first query with X, second query with X, and all the way through like, the last query point with X. And here the query time is like just 1 because you just do a lookup. Okay. And then another option is just like store the inner products with the basis vectors. And then here the query time is like n because you may need to know the inner products with all the basis vectors. Oh, by the way, by basis I mean when I mention EI, it's like the ith position is 1 and 0 elsewhere. Okay, the standard basis vectors are like, yeah, it's like quote unquote standard because I'm thinking of it this way. Anyway, so hopefully that's clear. And also throughout this talk, think of this capital set Q to be of size at least n square, some quadratic or like some polynomial in n. Okay, could be much larger, and I'll get to that. But this is something to start with. Okay, good. And let's think of some example query sets. One is like the whole space itself can be any point in F2 to the n. Another is like think of all Hamming weight 2 vectors. This could be one. Another one is like maybe the set of all square root n by square root n matrices. And what I'm going to do is like take these square root n by square root n matrices. Set of all rank 1 square root n by square root n matrices is what I think of. And you can just think of these matrices and then expand, unroll them into a vector. And then now you get a n length vector and you want to take an inner product. Okay. Sorry about the typo there. And another option is like the usual, like the standard partial sum type of problem where like you want to know the parity of the first I indices of your data X. Okay. So your query is going to correspond to like, all vectors where like until some coordinate I, they're all 1 and beyond that is 0. Okay. Good. So hopefully this, the setup is clear. Okay. And let me define one quantity called LT of Q and S, where like, which is the smallest query time among all spaces data structures. Okay. And what we really want to understand in this space is like for a given query set Q, how does the query time, the size of Q, the dimension of the ambient space that it lies in, and the space of the data structure are all related. Okay. And I'm going to be looking at it from a lower bound side, and I want to say that like for explicit Qs, the best known lower bound is roughly log size of Q divided by log of S over n. Okay, so since we are going to be thinking of the space to be like linear in n or 2n, you can roughly think of the query time lower bound for explicit sets to be roughly log q. Okay, that's the best we know. And I'm ignoring constants when I write this statement. Okay. And in fact, the interesting thing is this is also the case for general data structures. You may imagine that like this is a very restricted setting where I'm like forcing you to only store inner products. Why should I do that? Maybe the model is not general enough, so you may want to go for like storing arbitrary bits. Even in that case, for explicit query sets, the best known lower bound is roughly log q. Okay, so in some sense, from a lower bound perspective, looking at linear data structures is interesting in the sense that like you actually have linearity, which is very nice, and you also are in a space where like the best known lower bounds match for like both linear and like the general case. It's one of the simplest models for which we still don't know how to prove non-trivial lower bounds. That's another way to say all that I said in the last 2 minutes. Okay. And as I said, since we'll be thinking of like the space to be 2n, the explicit lower bound, the best known lower bound for any explicit set q is log q. Okay. And good. So this is actually a good stopping point for questions if there are any, in the sense of like the model definition and what the question that we're interested in and so on. And I see some 2 notifications, but I'm not sure what they are.
So Arkadev is just commenting that this means that you don't get anything if s is equal to n plus little o of n. Is that right?
Why is that the case? Maybe he should.
Arkadev, you can speak up.
Okay. Hi, Shiva.
Hello.
Arkadev here.
Yeah.
So sorry, because you just said that there's a log. I mean, where's your lower bound?
Yeah. The s over n.
So s over n. So if s is slightly larger than n, then you get a negative number there, right, or something like that.
Like you mean s is n squared, or like?
Well, even n plus some little fudge.
Yeah. Why is it negative? It is log 1 plus some little number.
Sorry. Yeah. I'm reading it n by s. Sorry. My bad.
No. Sorry.
Yeah.
And also, I'm always assuming s is at least n because.
Sure.
Yeah.
No.
Yeah.
I mean, Sorry. Never mind.
No problem. Yeah. Perfect. Any other questions at this point about the model and yeah. Good. Okay, so now so far we have seen like rigidity that's defined for like n by n matrices, but I'm going to use a notion here that's more convenient. That's was defined by Alan, Panigrahi, and Yakhanen, and this is about which talks about defining the rigidity of a set instead of an n by n matrix. But of course, I'll tell you, they're all the same. So. What we want roughly is we want a subset of f2 to the n that's far away from any low dimensional subspace. Okay, and if you pick a random set of size n squared, then it would have this property where it's far away from say n over 2 dimensional subspaces. Okay, but as before, we are really interested in finding explicit sets. Okay, I'm sorry about the background noise. Hopefully, yeah. Okay. Good. Great. So what am I looking for? You have the set Q that lies in F2 to the n. You just like write a matrix which is of dimension size of Q by n. And then what I want is I want this to be not be equal to a low rank matrix plus a sparse matrix. Okay. So previously size of Q was thought of as n. And you look at an n by n matrix and you don't want to write it as like a sum of low rank and a sparse matrix. But here I'm thinking of, Q to be of arbitrary size. Okay, it's even n square, n cube, some large number. Okay, good. So formally what we want is we call a set Q to be RT rigid if for every R dimensional subspace V, there is one point in Q that is at a Hamming distance of at least T from this subspace V. Okay. In other words, you look at this matrix Q, and you will not be able to write it as like sum of A, which is rank R, and B, which is T sparse in terms of the rows. Okay, so one distinction that I have to talk about here is like from like Valiant's original notion of rigidity is like the average case versus worst case. Here, all I care about is just one point being far away. But in the case of Valiant, you want like most of the points to be far away. Okay. So the main difference is like the size of the set can be arbitrary, or like the number of rows in the matrix can be arbitrary. And you're not expecting an average distance bound from in terms of the sparsity, but you're looking for like the worst case. Okay. Is that hopefully that was clear? If not, like, yeah, please stop me. Okay. Again, here the question is again very simple. We have multiple parameters like R, T, N, Q, size of Q. So what's the relationship between them? You know, for a given Q, how do you think of these parameters to be related? Okay, that's the question we want to understand. Okay, great. Okay, so going back, so so again, we're like, I want to tell you what like the best known lower bounds for like explicit sets Q are, and it's nothing but it's forget the second term in the minimum. The first term is roughly N over R times log size of Q over R. Okay. In terms of rigidity that we saw in terms of the Valiant's notion, we actually saw the lower bound to be N square over R times log N over R. So size of Q was just replaced by N. So now you think of some arbitrary size set. And then instead of N square over R, it's N over R because you're not, it's like average, worst case over average. There you are counting the distance of all N points from your subspace. Here you're only counting the distance of 1 point from the subspace. Okay. Hopefully that was okay. Great. So this is again where we are. I should also mention that apart from the previous discussed results of Friedman and SSS, there's a result due to Alan, Panigrahi, and Yakanin, where they actually do provide rigid sets that match this lower bound, but also has an upper bound. And later, Alan and Cohen came up with using expanded graphs. And I think in some cases they were tight, in some they were not. That's like take it with a pinch of salt, but that's all I remember at this point. Okay. I believe maybe the one for like the epsilon bias sets were tight for some parameters, but yeah, anyway. Good. So hopefully and like, again, if you sometimes or most of the times when I am thinking of these lower bounds on rigidity for explicit sets, I'll think of the rank to be N over 2 or constant times N. In that case, all you have is log of Q, size of Q over N. Okay, and if Q is like quadratic or something, all the lower bound that you have is roughly log Q. Okay. Good. Any questions at this point? No. Okay. Great. So so this is like roughly the first two set of notions or definitions that I need for like the next part of the talk. So essentially, at this point, like there's been a lot of progress in like data structure lower bounds, but roughly everything got stuck at this log Q barrier or bound, and it was not clear why we couldn't prove better lower bounds. And this very nice result of like DeVere, Golonar, and Weinstein, they showed that like it is probably for a good reason, or like that we are not able to go beyond log Q. So what they said was like, if you have a query set Q that is explicit, and if you can show a lower bound that's better than log Q times log N, then you'll be able to find a semi-explicit set which actually beats the current rigidity parameters for you. In that, what they show is like you can find a set Q prime in F2 to the N prime space that is rigid in terms of the rank parameter being like N prime over 2, and then but you get a rigidity lower bound or the sparsity lower bound that's better than log Q. So log Q again was like the best known for like the explicit sets in terms of rigidity, and in terms of like data structures, you are like again stuck at log Q. So this says that if you get beyond log Q times log N, then you actually do obtain at least semi-explicit rigid sets. Okay, so is the statement of the theorem clear? So we don't, like, ideally we would want to say something about like, what if I get just slightly better than log Q in terms of linear data structure load bonds? We don't know that yet. But here they say that like, if you get slightly beyond log Q log N, then you have, new rigid sets. Okay, good. Any questions on the result at this point? No? Okay, so my plan here is to actually give an outline of that proof, but not how they presented it. Essentially, I'm going to, they actually proved a much more general result in terms of a connection between inner and outer dimension of matrices. And, but what I'm going to do is like, I'm going to pull out a lemma that was like implicit in their proof and just going to show how to prove it, okay? Which should get us to the result. Okay, sounds good. So the lemma claims the following. It says that like, for some parameter t that's more than log n, if the query set is not n over 2 comma t over log n rigid, then you'll be able to find a set q prime such that the dimension of q prime is like at most n over 2. And if you think of the linear data structure query time for q with space 2n, that can be upper bounded by the linear data structure query time for q prime and space n plus this t over log n. Okay, so let me like maybe recall what this LT term is. LT is nothing but of q comma 2n is like for the query set q, look at all data structures that have space 2n. What's the best query time that you can have? Okay, so essentially this, what this is saying is if the set you started off with q was not rigid, then you actually have a way to upper bound the query time of this particular set in terms of a related set and with like a little like, overhead of this t over log n parameter. Okay, so one quick comment is like, you can think of q to be full dimensional in the sense that like the rank of or the span of all the vectors in q is like, it covers the full space. If not, you can find a smaller subspace and like do this argument. And the nice thing that you think of what's going on here is like the dimension of q was n, and you are like looking at space 2n, and then now you get to another q prime whose dimension is n over 2, and you're looking at like space n. Okay, great. So why is this lemma very important? Because now you can recurse on this q prime until you hit a constant dimension. So in the process, either you will find a rigid set, or you would have shown that this linear data structure complex, the query time for this query set q is at most t plus some order 1 terms that comes from this constant dimension set that where you stopped. Okay, so this says that like if you actually had a lower bound on LT of q comma 2n, then you cannot have this upper bound. Then there was some middle point where you would have stopped, where you would have found a rigid set. So that's the rigid set that you want. Okay, hopefully that is the recursion, or like how this lemma gives you the result is clear. And also I am not talking about the explicitness of q prime or how you identify it, but it's an exercise to actually show that like you can actually do it with just NP oracle calls. Okay, so hopefully that's fine. Let me tell you how to prove it. Okay, so now you have the set q that's not rigid, and you want to find an efficient way to actually, or come up with an efficient data structure for it. Okay, so since q is not rigid, you can find a subspace V of dimension n over 2, such that for every point in q, you can express it as a sum of two vectors, one that is in the subspace and the other whose distance from the subspace is small. Okay, so now you define this set q prime to be all the points within the subspace V that you found. The closest points of the vector of your query set within the subspace. So clearly the dimension of this set q prime should be at most n over 2 because the subspace V is of dimension n over 2. Okay, good. The next step, what do? is how to compute, or for the part B is like when you want to compute q times x, you actually write it as like vq times x plus uq times x. And for the first part, you use like you recurse, or like you use the data structure for q prime to compute that query. And for the second one, you just store the standard basis vectors, inner product with the standard basis vectors. And you know that the sparsity is small, the distance is small. So you should be able to, query them, or like compute that query with like only t over log n accesses. Okay. So hopefully this was clear. So essentially all I'm saying is you start with a non-rigid set. It gives you a recipe to actually, or like have an efficient data structure if the set you start with is not rigid. Okay. Good. So just to recall what we saw, the important thing is like and you lose the log n because every time you're only expecting, or like you lose this t over log n factor in terms of the additive term. So hence the log n overhead. But yeah. And also I should say that like their proof is much more general, and then like they essentially show a connection between inner and outer dimension as to how to do it, and then apply it to data structures. And also they prove connections between other type of data structures in rigidity. And also they have a connection to the regular, the variance notion of rigidity, and so on and so forth. Okay. Good. So this is actually a good stopping point for questions, if there are any. And I can, because for the second and third part of my talk, I'm going to introduce a few more definitions before I do proofs. So also probably I'm speaking fast and I'm going fast. So yeah, please stop me with questions. Yeah. So I'm assuming everyone's happy and like, yeah, the proof is clear. Good. And good. So this roughly tells you like the connection between linear data structures and rigidity. Okay. So now I'm going to tell you another connection between, again, linear data structures and rigidity, but this time using a different data structure model. Okay. As before, we again want to store an n-length vector and compute queries of the form q times x. But then the way you store it is different. You store the input asses x1 through xn, and then you get to store r separate inner products. Okay. And r is strictly less than n here. And the way you compute the query is you read a subset of the of all the bits that are being stored so far. Okay. So you have to store the input asses along with storing r extra inner products. So this is the systematic linear model. And actually this dates back to Valiant's common bits model. This is how he defines it, but not it's for not just linear functions, but for general functions. And then later, Galen, Milterson, and also a recent paper of Chakrabarti, Kama, and Larson also do this. And I'll tell you the slight distinction in them in a bit. So here, there are two parameters that we care about. One is the number of bits that you, redundant bits that you store, or the number of extra inner products that you store here. And then here the query time is defined to be only the number of accesses to X. You can essentially read the whole of A1 through AR, the inner products of A1 through AR with X for free. All you'll be charged for is accesses to, the input itself. Okay. And the distinction between Galen-Milterson and the CKL result is that like in Galen-Milterson, they also charge you for like accessing these redundant bits. But we're going to work with this model where like we are not going to charge you for that. Okay. So so that's the model. Hopefully that's clear. And good. So any questions on the model? No? Okay, good. So now let me tell you a data structure upper bound in this systematic model. Oh, I see a question. notification is that.
Yeah, so Arvind's question, Arkadev's question is, this is a linear version of the succinct data structure, this comment.
Yes, correct. Oh, yes, thank you. Yeah, I am not able to access my presentation. Yes, so this is usually referred to as also the succinct model. But the distinction between succinct and here is that in succinct, you are allowed to store n plus r bits, and the first n bits that you store doesn't have to be the input itself. Here I'm enforcing that the first n bits you store has to be the input, but in the succinct model, you don't have that feature or like that restriction. Okay, that's one distinction, but yes, this is again a further restriction of the succinct model. And it's also usually referred to as succinct because the number of extra bits or R bits that you store is usually thought of as little of n. And so that's why it's succinct in the sense of like you store literally like whatever entropy of your input is needed plus little of that entropy. Okay, good. Yeah, thanks. Great. Okay, so now let me tell you how if the query set Q is actually not rigid, then you can actually get an upper bound in this particular model. Okay. By the way, for some people who just saw this model, they would have already realized that like this is equivalent to the rectangular rigidity that I defined earlier. That's the punchline, but like, yes, I'll show it to you in 2 steps. Okay. Now I'm saying this because like someone in a talk I gave jumped and said that these are equivalent. And yes, these are equivalent, and bear with me, in like 2 minutes, I'll show you the equivalence proof. Good. So yeah, so let's say that this query set Q is not rigid in our sense. So essentially you can write this Q as a sum of low rank matrix plus these sparse rows. So now how do I get a data structure out of this? The redundant bits that I'm going to store are nothing but inner products of the basis of this matrix A, or like the row basis, and the queries now can be decomposed as like AI plus BI, where AI is a row in the matrix A and BI is a row in matrix B, and then the inner product, of course, is nothing but the inner product of QI with X is nothing but inner product of AI with X plus inner product of BI with X. So now in the query time, I told you that it's only accesses to the redundant bits that you're going to be charged with. Only accesses to the input that you're going to be charged with. So all the accesses that have to be done in computing BI times X is what matters. And since this matrix B is T sparse, you have T row sparse, then it has to be the case that you only access at most T bits every time. So this tells you that like if the query set Q you start with is actually not rigid, then you have an efficient data structure in the systematic linear model. Okay, good. And then in joint work with like Rashtian, we actually show that these 2 models are equivalent. And formally, what we show is like if Q is like RT rigid, Q is RT rigid if and only if every systematic linear data structure with redundancy R has query time at least T. Okay, so essentially a lower bound for the query in the systematic linear query model implies a lower bound for like the query rigidity for Q. Okay, good. This is the same statement in like pictures or boxes. If you have redundancy R and query time is at least T, then this query set has to be RT rigid. Okay. Good. So I showed you one side of the proof. I'll show you the okay. So before that, here again, of course, due to rigidity, like even in the systematic linear lower bound side, the best known lower bounds are like exactly match what you have for rigidity. Like the query time must be at least n over r times log size q over r. So that's the best we know. And we also know of explicit sets that are given in like Gall-Milterson and also CKL that match these bounds. Okay, that's good. And okay, so let me show you the other side of the proof of the equivalence. In that if the set is actually rigid, then every systematic linear data structure with redundancy R must have query time at least T. Okay. So I'm going to hand wave a little bit maybe here, but I'm not too sure. Yeah. So let the redundant bits be given by A1, inner products of A1 through AR times X, and let define U to be the span of A1 through AR. And we know that like U is of dimension R, a subspace of dimension R. Since the query set Q is rigid, we can find a query point Q star that is at a distance of T from this subspace U. Okay. And now the claim is that to compute this, the query on Q star, you need at least T accesses. And the way you prove it is by saying that, say the query accesses like, all of A1, inner products of A1 through AR with X, along with like the inner products EI1X all the way through EIKX for some parameter K. Then you look at this space U prime, which is the span of A1 through AR, along with also adding the vectors EI1 through EIK. And then you must be able to prove here that the Hamming distance are like this point Q star lies in this space U prime. So if not, you can actually find another point X prime where the query Q star inner product with X prime is actually going to be different from the inner product of Q star with X, but then the algorithm will read the exact same bits and will have the output wrong. So here we're assuming that the algorithm is correct always. So if this does not happen, then you must be able to, the algorithm must be wrong if this is not the case. Yeah, the takeaway is that like the way the proof works is like you take this vector that's the farthest away, and then on that, like essentially all the algorithm can do is like within the subspace, it has all the freedom because it can read all of like A1X through ARX. But from there on, the best it can do is take the shortest path in order to reach the point you want. Okay, good. Any questions on this equivalence proof so far? No? Okay, good. Great. So okay, good. Also, we get some consequences for linear data structures. What I want, that I'll point out using this equivalence. What we get is if the query set, if you actually end up proving a query time lower bound on the linear data structure of like roughly little omega of like square root of log Q times n, then you'll be able to find a rigid set that's better than K over 2 times. I think it's like it's a typo there, but it should have been like little omega of log size of Q prime. So essentially, like in contrast to like DGW, what we say is like if you can prove polynomial lower bounds on the query time, then you actually get explicit rigid sets instead of like semi-explicit rigid sets. But then like you need like polynomial lower bounds on the query time and not just log n improvement or like anything better than a log n multiplicative factor over what we currently know. Okay, so this is essentially saying if you can prove really strong data structure lower bounds in the linear data structure model, then you'll get explicit rigid sets. Okay, and this actually follows from a simple observation that if you have a systematic linear data structure with redundancy R and query time T, then you also have a linear data structure with query time T and space n plus R. Because all you do is any systematic linear data structure is also a linear data structure that reads the whole of the redundant bits and you charge extra R for it. Or like, yeah, sorry. So there's a typo here or a bug here again. So it's like, it's T plus R because you read at most, you read like T from the query time and also you read the redundant bits. So it should be like, yeah, T plus R. But it's as simple as that, like, yeah. And then you plug it back into the equivalence and then you have to see as to the parameters as to where you get something new in terms of rigidity bounds. So that's all there is. Okay, good. So hopefully that was clear. Any questions? I'm like getting towards the last part of the talk where I'm going to prove rigidity lower bound, and hopefully, and also the proof is going to be very simple. So, great. Okay, so now let's look at a interesting problem, which is called the vector matrix vector problem. So the goal is to actually design an efficient data structure for where you actually have to store a square root n by square root n bit matrix. And you want to be able to compute queries of the form U transpose MV, where U and V are like square root n bit vectors. Okay. Another way to think about it is like, yeah, you want to do this like matrix multiplication with these vectors U and V. This is nothing but an inner product over a different space. The way you can think of it is like, you can think of UV transpose as a matrix that you want to multiply with again M and take the trace. Another way to think about it is just look at this UV transpose or VU transpose matrix, make it an, this is a square root n by square root n matrix, make it an n length vector and make your matrix M an n length vector and do your normal inner product. Okay, so hopefully it's essentially what I want to say here is computing these U transpose MV problem queries is like a linear query, and it corresponds to a linear data structure problem over the F2 to the n space if you just unroll the matrix into a vector. That's all. Okay, good. So in the systematic linear model, what do you want to ask? You want to be able to store like R redundant bits, which are nothing but inner products of like matrices A1 through AR with this input matrix or data that's M, and you want to compute on like queries UV, this inner product U transpose MV. Okay, and you'll be charged for accesses to the input matrix or the data M. Okay, good. So what we show here is actually a new lower bound in the systematic linear model for this problem, but by proving a rigidity lower bound for the vector matrix vector problem. Because of the equivalence that I showed earlier, a rigidity lower bound will also translate to a like a data structure lower bound. Okay, and here the query set corresponds to the set of all vectors that come from like these rank 1 matrices. And again, like when I'm talking here, sometimes I'll switch from matrices to vectors, and by that I mean is like just unroll your matrix, okay, into a vector. So what we show is like in joint work with like again Cyrus is if this query set is RT rigid, then the rigidity, the distance parameter T must be at least n to the 1.5 divided by R. Okay, and I have to point out that this is like a log n factor improvement over this previous result of CKL, but they actually proved this lower bound directly on like the data structure problem, which again, because of our equivalence, translates to a rigidity lower bound. And here we are able to improve by a log n factor. But the nice thing is like I will actually show you the proof in like in 2 slides. Yeah, so that's the, yeah. You don't have to know data structures, you don't have to know other connections, but I'll just tell you as a like a linear like problem or like a linear algebra problem about rigidity, I'll tell you how to prove this lower bound directly. Okay, so that's the plan for the rest of the talk, and I have about 15 minutes. I'll probably be done in like 5 to 10 minutes, but yeah, that's fine. Great. So again, like let me tell you what the key lemma here is. So for every R dimensional vector space V or subspace V, I'm going to show that there is a square root n by square root n matrix whose rank is small. In that it's at most 2R over square root n, and the distance of this matrix from the vector space is like, you know, still large. It's omega n. Again, by distance here, I am talking about vector spaces that are in F2 to the n, but this M is a matrix that's square root n by square root n dimension. Again, like unroll the matrix and you get a vector, and you want to look at the Hamming distance. Okay. Okay. So now let me show you why this is sufficient. If M is small rank, then you can write M as sum of rank 1 matrices, where like the number of rank 1 matrices is at most 2R over square root n. Since this M was like large distance from V, one of these MIs must also be of like large distance from V. And that's all. That's just direct averaging, and you get like n to the 1.5 over r, the distance. Okay, so essentially the mi that you have found is a rank 1 matrix. So that's one of your query point, and that's this much distance away from the vector space. Okay. Also, I should say that like in this lemma, if you remove bullet point A, then just finding a matrix or a vector that's far away from the subspace is just basic counting. The trick, or like the important point here, is also finding a vector or a matrix that's like small rank. Okay. Hopefully that was okay. Because if you just remove point A, it's like yeah, you just want to find a vector that's far away from a n over 2-dimensional subspace or something, and that they exist, like a lot of them exist. So good. So let's look at the proof. This proof actually is inspired by this result of Alan Panigrahi and Yakanin, and also slightly has a direct sum flavor. So, but these are all buzzwords, so I don't want to emphasize. So I'll just tell you the proof, okay? And then you can decide, whether like as to what category it falls in. Good. So you define this the vector space V that we start with. We know it's like r dimensional, so it's a span of like r vectors. So you write these vectors down, and I'm going to now define n over 2r different subspaces, which are nothing but projections of this subspace V onto, say, the first 2r coordinates, the next 2r coordinates, and so on and so forth. Okay, since the original vector space you started off with was dimension r, each of these VIs also are dimension at most r. Okay, so far so good. Now the key claim is you can find a vector V prime in this 2r dimensional space that is far away from all these subspaces. This is essentially again basic counting. So each of these VI subspaces are dimension at most r, and there are at most n of them. So by the usual counting argument of like bounding the number of points within a radius of say r over 100 from every point is going to be small. So even if you take the union of all those points, you wouldn't have covered the whole space of f2 to the 2r. So you'll be able to find such a vector. Okay, so all that you have to know is like there's a vector that's within the 2r dimensional subspace, or like space that's far away from all these subspaces that you have defined. Okay, now what do you do with it? I'm working, this is like a vector over 2r dimensions, but like I want an n length vector that's far away. So what you do is simple. So you just like concatenate one with each other, like multiple copies of it, and you form this big vector V of length n. Okay, and by definition, we know that like the distance of this vector V from the subspace capital V must be still large, because each V prime is of distance large from like the VIs that we define, the smaller subspaces. So the overall vector V must also be of like larger distance. Okay, so this is very good. So this satisfies property B, because I'm going to take V and make it a matrix by just like taking this long vector of length n and then cutting it at square root n pieces, and then stacking one row after the other. Like the first square root n indices is like the first row, the next square root n is the second row, and so on. But the nice thing you'll notice is each vector V prime that was used corresponds to roughly 2r over square root n rows. And then this block of the matrix is repeated entirely. So the rank of this whole matrix cannot be more than 2r over square root n. So essentially what I did was like look at a smaller, like break this whole subspace into like smaller subspaces and find a point that was far away from all of them, and then put them back together. But when you put it back together, there's a nice property that like you have a lot of repetitions in the rows, and hence the rank cannot be too large. So the rank is at most 2r over square root n. So this gives you what you want. So this is like a direct sum, as I said, because like I'm looking at like sub problems and then putting everything together in like a nice way. That's all. Okay, good. So that is all I have, and just to recall, this is what we proved is like if Q is RT rigid, then like T is at least n to the 1.5 over R. Good. And let me just conclude with some open questions. Actually, it'll be interesting to prove better rigidity lower bounds for this UV transpose or these class of rank 1 matrices. And the nice thing is, like, if you do not want to think of rank 1 type matrices, this also roughly corresponds to the generator matrix of a Reed-Muller code of degree 2. That could be another candidate to think about, and especially in terms of like rigidity of these like large sets, because the set here I'm defining is like not polynomial in the size, polynomial in n, but it's like 2 to the square root n roughly, or 2 to the 2 square root n. So even there, it's open to prove any better lower bounds. And the other one would be to actually improve the explicitness guarantee in DGW. The like a strong data structure lower bound only gives you a semi-explicit rigid matrix that is in P to the NP. So can we improve the explicitness guarantee there? And also, like, are there any rigidity implications if you just want to like prove a little omega log Q lower bound for any data structures instead of log Q log n? Okay, yeah, that's all I have actually. Thank you.
Thank you very much. Yeah. We have some time for questions if there are any.
Hi, Shiva.
So,
sorry, Amay, go ahead. Yeah.
Oh, okay.
No, you go. Okay. I'll ask you one question. This by Josh and Liji about this construction of rigid matrices. Does that framework imply new rigidity lower bound for this kind of rectangular rigidity? And yeah, and what are the implications of it to data?
I actually don't know. Yeah, to be honest, I actually don't know. Yeah.
Okay.
Yeah, but like the thing is, like at least the way I think about it is like I'm not sure if there are other connections from rectangular rigidity to other problems, but like DGW, they show that like rectangular rigidity also implies square rigidity. You probably lose a log n factor. So anything new that you prove in like that is very strong in the rectangular rigidity world should also give you something in like the square rigidity world.
Normal rigidity. Okay, I see.
Yeah. So they're like they're almost equivalent, but for the log n factor. So yeah.
I think I missed something. What would you say square rigidity? So you have this rectangular rigidity RT.
Correct. Yeah. So by square rigidity, I mean like the size of the set is exactly n, and you are looking at average case sparsity and not worst case sparsity, like original definition of Valiant. Yeah.
Okay.
Yeah. So they have a way to like go from rectangular rigidity to the original definition of Valiant, where you only lose a log n factor roughly. And yes, so it's still like, so anything very strong that you see here will also imply something in like the square case. So yeah.
Okay.
Yeah.
So I had the same question. No, I had the same question.
Exactly.
Yeah.
I see. Okay.
I see.
And there's also a comment from Arkadev. Rectangular rigidity was also used by Grigoriev and Razborov. Is that right? I'm not aware of this.
Oh, I didn't know. Maybe I'll ping you for the link and I can like add a reference. Yeah.
Okay, I have one other question. So all of these are like data structures. These are all deterministic data structures, right? I mean,
correct.
So would there be a suitable rigidity analog if you want to look at some sort of probabilistic data structures and if you want to prove lower bounds for those?
Right. So yeah, I actually don't know, but it's a good question in that like you probably, I should say I don't know. Yeah, I think that's yeah, of course, like by probabilistic, I'm assuming you mean also where the data structure makes an error, because otherwise it's like the same deterministic, but yeah.
But Siva, if I might just, so wouldn't it be true that would it be too much to expect that basically rigidity lower bounds actually imply randomized lower bounds as well? Because you're making some errors, so you can, so you can convert the randomized problem to a deterministic problem with perturbations, right? And then somehow you can't you absorb that perturbation in the rigidity definition?
I see. Yeah.
Yeah, if I may. Yeah, so in general, when we're talking about linear problems and stuff, right, a mistake means you're wrong on at least half of the inputs, right? When we're talking about you're not computing correct.
Okay.
So yeah, you shouldn't expect small error, but for large errors, you can do exactly what Arkadiev says. If you have a large error, that essentially means you differ by some like low rank metrics. So yeah, no, this plays nicely with rigidity definitions. Just probably you don't want data structures that are wrong on like all but a small fraction of inputs.
Yeah, that's it. Okay, that makes sense. Thank you. Yeah.
Yeah, thanks. Yeah.
Okay. Any more questions or comments?
Sorry, so what's the best known lower bound for the vector matrix vector problem that we know today?
In like what model?
Let's say the linear model. So
yeah, so it's log q square root n for like linear space, or square root n or log n for polynomial space. Yeah.
Okay.
Yeah, if you think of it, maybe like people like to think of it as like the input being n by n matrix. So in that case, an n lower bound or n over log n lower bound.
Right.
Yeah. Yeah.
And what is the best known upper bound in a data set achievable?
N square over log n or log square n for like polynomial space.
You can shave off log square n from the brute force.
Yes. Yeah.
I see.
Log n definitely. I think also log square n, but yes. This is the famous 4 Russians algorithm.
Right. So, but okay.
Yes.
So I mean, sorry, I got a bit confused. So to prove a log square n lower bound would certainly give you. Is that doesn't your result say that will give you rectangularly rigid matrices?
No. So okay. So in case of this UMV problem or the vector matrix vector problem, on n by n matrices, you want to prove a lower bound of n times log n or log square n.
Yeah. No, but how much can you prove without hitting the rigidity barrier?
That's right, n log n.
N log n, okay.
Yeah, for linear space, n log n.
And that's still not known, right?
That's still not known, but you should keep in mind that like the rigidity implication is p to the np, where p is a function of the number of queries in the set. So it's like, again, 2 to the n kind of implication there in the p. So you're like, yeah.
No, but I'm saying if I completely, okay, I see. Yeah, no, makes sense.
Yeah. Yeah, for like without like if you want explicit stuff, I think n to the 3/2 or something is what you need. Essentially, you need to beat the systematic lower bound to get something in the explicit regimes, but like semi-explicit regimes, it's like extra log n factor.
Okay, thanks.
Yeah.
Okay, so I think there don't seem to be any more questions, comments now. So let's thank Shiva once again. And in fact, let's thank all the 3 speakers of today's workshop, and look forward to seeing everybody again tomorrow. I think there is a message from FSTTCS that the Gather Town channel is also open if anybody wants to head over there.
Right.
And otherwise, we're done for the day. I don't know whether any of the organizers want to say something more right now.
No, I guess that's all for today. And yeah, we'll continue this workshop tomorrow at 8.
Thank you. Bye-bye.
Sounds good. Bye.
Amay, can you just wait a minute?
Yes, I was about to ask what's the protocol.
So can you stop the stream? You still have the host. Can you stop the stream?
Okay, so first stop the stream, the live stream, right?
Yeah, live stream.
Okay,
And
so stop live stream. Yes.
Yeah, tomorrow you are going to run the show, right? I mean, you are going to run the. Will be managing the.
Yes.
So can you, if you press it.